So I picked out these.
I'm gonna identify.
I picked out these.
This is my chapter 10. I'm gonna identify this. My chapter 10. This is my
and number
10
1
is my chapter 10.
Which of the following should have the lowest boiling
number
point?
1.
So which of the following should have the lowest
boiling point is the one that has the weakest intermolecular
So the one that has the
force.
lowest boiling
Traction
point
between
is the one that has the weakest.
So you look for intermolecular
Process of
force.
elimination.
Traction between
You can throw out the
So you look for-
ionic compounds.
Yeah.
Process of
So
elimination.
A is out.
You can throw out the ionic
And,
compounds.
Yeah.
All right, so B
A
is out
has a very strong
and
dipole.
right,
B
HF is a strong
Is
dipole.
has a very so it's probably not a good candidate.
Dipole,
Why?
right? HF is a strong dipole.
So it's probably not a good
Yeah,
candidate.
because it's like this.
Why?
Yeah.
Right, and it's got a dipole like that. Yeah, because it's like this,
Yeah.
right?
And
And it's got a
C
dipole
is
like ammonia. And it's like, we learned in the first semester. And C is ammonia.
H here,
And
H here,
it's like,
H here.
we learned it
the
there,
first
so its
semester.
dipoles like that. H here, H
So it's
here,
gonna
H
have a
here,
stronger attraction.
There, so its dipoles like that.
Water,
Of course, is obvious.
so it's going to have a stronger attraction.
It's got a strong
water,
dipole.
of
course, is obvious.
And potassium is a metal.
It's got a strong dipole.
And metals have a very high
And
boiling
potassium
point.
is a metal.
Most of them. Mercury is probably an
And
exception.
metals
have a very high boiling point.
So the only one that
Most of
fits, let's see, wait a minute.
Mercury is probably an exception. I'm in the wrong one.
So the only one that fits, let's see, wait a minute. That's been happening to me all day.
I'm in the wrong one.
Yeah.
Let me see. C isn't, yeah, okay.
Yeah,
That's
that's
been
good
happening to me
till
all
Water
day.
was.
Water
me
is E. C is,
Yeah,
water is
okay.
E.
I was good till there.
Water was.
Water is E. D,
Yeah,
water is E, is nitrogen.
That's your best candidate. Because it's not
D
dipole. The
is
only access it
nitrogen.
has to
That's your
intermolecular
best
forces
candidate.
is, because it's
Abundance
not
dispersion
dipole.
forces.
The only access it
Very,
has
very,
to
very
intermolecular forces
So that would
is
have your lowest
abundant
boiling
dispersion forces.
And in fact, its
very,
boiling
very,
point
very
is
weak.
minus 100. So that would have your
degrees
lowest
C.
boiling point. In
Very,
fact,
very
its
low.
boiling point is minus 195 degrees C.
Very, very low. All right, number 3. All right, number 3. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? When a water molecule forms a hydrogen
Well,
bond
if you
with
got
another water molecule, which
like
atoms are
this,
involved in the
And
interaction?
this is going to be the positive side. Well, if you guys, this is going to be the negative side. Like this.
Of the hydrogen
And
bond.
this is going to
And
be
this
the
can be
positive
either
side.
nitrogen,
This is going to be the
oxygen,
negative side.
or of the hydrogen bond.
Fluorine. And this can be either nitrogen, oxygen.
And how do they
or-
orient themselves?
Well, they orient themselves so that the positive is like this, and then negative
And
is
how
like
do they
that.
orient themselves?
Positive
Well,
is
they
like
orient
this.
themselves
So that the positive is like this.
And that's how you
negative
form
is
the
like
bond.
that. Positive is like
Between
this.
two separate molecules.
And that's how you.
So a
form the
hydrogen
bond.
bond from one molecule
Between two separate
and
molecules.
oxygen from the other molecule.
Oh, we're
So a
talking about
hydrogen
water
bond from one
molecule.
molecule and an oxygen from the other molecule.
this would be
Oh,
the
we're
oxygen.
talking about water molecule, okay. You form
So this would
bonds
be the
between the
oxygen.
two molecules. And
They're electrostatic.
you form bonds between the
Positive on
two
this side, negative on
molecules.
that side.
And that's why
they're
B works the
electrostatic.
best.
Positive on this side, negative on that side.
So that's why B works the best. Let's see. Okay, we're gonna use drawings in above here.
Let's
And
see.
number 4, okay, we're gonna use drawings
Focuses
in
on the third
above
drawing.
here. And number 4,
Focuses on the third drawing.
so let's look at there we go. So which of the following statements
So let's
is
look at the-
incorrect concerning
There we
this
go.
drawing? Electrostatic
which of the
interactions
following
exist between the
statements is
molecules. Incorrect concerning this drawing.
Yeah.
Electrostatic
slight
interactions
positive and
exist
slight
between the
negative charges.
molecules. So A is true.
Yeah.
Because they have slight positive and slight negative charges.
How about
So
B?
A is true. The molecules find the best compromise between attraction and
How about
repulsion.
B?
Yeah, the
That's
molecules find the best compromise between
How about
attraction
C?
and repulsion. These molecules
Yeah, that's
exhibit
true.
ionic bonding.
How about C?
No. These
They're
molecules
intact
exhibit
molecules
ionic bonding.
with
Positive and negative
No.
ends. They're
If they
intact
were
molecules
ionically bound
with, you'd have separate ions. Positive and negative ends. Right, in this case, the
If they
hydrogen
were
would be separate,
ionically
the chlorine
bound,
would be separate.
you'd have
from that.
separate ions
With its Right, in this
particular
case, the
bond.
hydrogen will be separate, the chlorine
mesmerizing?
will be separate from that.
Yeah, bulletin
With
tips
its-
in it.
Yeah, it
particular
does.
bond.
It's
Yeah, I
got
thought
bullets.
so.
That
I saw it
mesmerizing.
bouncing around. I was like, why can't you have bulletin tips in
So
it?
C is the bad
Yeah,
one.
it does. It's
Yeah,
got
I
bullets.
thought so. I saw it
Two of the
bouncing
above
around.
are
I was like,
incorrect. I guess we have to go to D.
So C is the bad one.
OCS exhibits
Yeah.
this type of
Two of the
interaction.
above
are incorrect. I guess we have to go to D. OCS exhibits this
S.
type of interaction.
"Hmm."
All right, so if
C,
the most
S.
oxygen and sulfur are more electronegative
All
than
right, so if
carbon,
the most
oxygen and
so they
sulfur
go
are
this
more
way
electronegative
and that way,
than
but they're not the same
carbon.
strength. Right? So they
Oxygen,
go this way and that way, but they're not the same
oxygen's going to
strength.
be is above sulfur, so
Oxygen, it's actually going to be overall.
yeah,
that
oxygen's going to be, so
is
you
above
should get a
sulfur,
similar
so it's actually going to be
type of
overall
interaction.
that direction, dipole-dipole.
So you should get a similar,
All right,
so the only one that's
type
false
of
is C.
interaction. Dipole-dipole interaction.
All right, so the only one that's false is C. All right, how about 6? All right, how about which best explains the following trend? If we're going from, notice
Which
those
best
are all noble
explains the
gases
following
and they're in
trend?
order from top to bottom.
We're
Helium,
going
neon,
from
argon, krypton, xenon.
Notice those are all noble
And the boiling
gases and
point
they're in order
increases
from top
as
to
you
bottom.
move down.
Helium, neon, argon, krypton, xenon.
So
And
the boiling
what
point
best explains
increases
that?
as you move down.
Well, it can't be dipole-dipole.
So what best
Because they're
explains
single
that?
atoms. Well, it can't be.
Can't be hydrogen bond because there's no
dipole
hydrogen there.
because they're single atoms.
Le Chatelier's principle
Can't be hydrogen bond because
has
there's no
nothing to do
hydrogen
with this.
there.
Le
So by
Chatelier's
process of
principle
elimination,
has nothing to do
we
with
can't
this.
say none of these because London dispersion does
So
work.
by process of elimination,
The bigger the
uh,
atom,
we can't say none of these because London
the more
dispersion does
probable,
work.
right, the bigger the atom,
Uneven distribution you have of
the
electron
more
densities.
probable. So the
Uh,
bigger atoms, you can have
Uneven distribution you have
more
of electron
instantaneous
density.
distribution of
So with the
electrons
bigger
this
atoms,
side,
you can
diffusion
have
this side.
more instantaneous
So that's why the
distribution
bigger
of
atoms,
electrons
as you go
this
down
side
the,
and diffusion
the,
this side.
noble gases.
So that's why the bigger
have the higher boiling
atoms,
points.
as you go down the noble gases, have the higher boiling points. Let's see, 7 and 8. Let's see.
Which of the
7 and
following
8
compounds
has the lowest viscosity? Okay, the lowest viscosity. Which of the
Of
following
those
compounds has the lowest
compounds that have-
viscosity? Okay, the lowest
Or
viscosity
elements
that
of
have
those
the
compounds
weakest
that have forces.
high
or elements
viscosity means
that have the
strong attractions.
weakest it forces.
Impedes high
flow.
viscosity means strong attraction.
So we look for the one that has the
impedes
flow.
lowest attractive forces.
So we look for
The one that
and
has the
of course you got water,
lowest
and
attractive
you got
forces.
HCl.
Those are polar
And
compounds.
of course you got water, and you got HCl.
Carbon tetrachloride,
Those are
nitrogen gas,
polar
and
compounds.
I'm not sure what that one is. Carbon tetrachloride, nitrogen gas,
probably diesel
and
oil of some kind.
I'm not sure what
It's
that
a
one is.
hydrocarbon.
CH3
It's probably
with a
diesel
CH225
oil
and
of some kind.
CH3.
It's a hydrocarbon.
CH3
Why
with a
is diesel
CH225 and
bad for the
CH3.
environment?
Why is diesel bad?
Why is diesel compared to gas bad for the environment? I don't
Oh,
understand.
after you burn it. Why is diesel bad?
Well,
Why are people so compared to gas? People are.
Oh, after you burn it.
Yeah, why?
well, you notice
Well,
that when you see a diesel engine running down the road,
Maybe it's just like flat.
The
well,
black
you
smoke.
notice that when
That
you
black
see
smoke
a
is
diesel
soot.
engine running down the
It's
road,
incomplete combustion. The black smoke.
that black
It's not
smoke is
completely
soot.
converted
It's
to carbon dioxide and
incomplete
water.
combustion. And
It's
diesels
not completely
usually don't have
converted to
catalytic
carbon
converters.
dioxide and water.
I
And
think it would clog them
diesels
up if you
usually
tried.
don't have catalytic converters.
But gasoline engines do. I think it would
catalytic
clog them up if you
converters,
tried.
and
They spew
but
out
gasoline engines
water
do, and carbon
and
dioxide
catalytic
converters,
and nitrogen
and they
gas. They spew out water.
so they're
and
only
carbon
pollutant.
dioxide
I
and
guess if
nitrogen
you
gas.
think in those terms is carbon dioxide.
So their only pollutant,
Yeah, but.
I guess if you think
in
in those
yeah, but it's
terms,
not.
is carbon dioxide.
So the diesel, people don't like the diesel because of the
yeah,
the smoke.
So the
unburned
diesel,
carbon.
people don't like the diesel because of the smoke. The
And then
unburned
there's the
carbon.
smell.
Yeah. And there's no name for that. no way
And then
either,
there's
but,
the
you know.
Well, yeah, the,
And there's no name for that
that's been the
noise
case
either,
from the
but, you
very
know.
beginning. when
well,
Adolf
yeah,
Invented the
the,
engine.
that's been
The diesel
that's been the
engine.
case from the very
It
beginning.
knocked.
When Adolf
invented the engine,
and that's just
the diesel engine,
artifact
from
from
the
the
explosion that takes place in each cylinder.
and that's just
Because the diesel is not
artifact
spark
from the
explosion that takes place
It's
in each
compression
cylinder.
heat initiated.
Because the diesel
No
is
spark in
not
there at all.
spark initiated.
It's compression heat
It's,
initiated.
if you get the high,
no
if you get
spark
the
in there at
compression
all.
ratio high enough,
Yeah.
then the heat,
It's,
as you
if you
compress
get
the
the high,
gas,
if
it
you get the
builds heat.
compression ratio high enough,
And that's heat is
then the
enough for
heat,
ignition. As you compress the gas, it builds heat.
remember your
And that's
gas laws?
heat is enough for
We
ignition.
had, PV over.
Remember your
NT
gas laws?
equals PV. We had,
T.
PV over NT equals P1. Well,
T.
if you got, if the moles are the same for both of them, which they will be. One, you can throw that one out. If you got, if the moles are the same for both of them, which they will be. The temperature is changing. Throw that one out. As we decrease the volume, as we go from smaller, this one to a smaller volume. As we decrease the volume, as we go from smaller, this one to a smaller volume. Volume decreases, but the pressure increases.
Yeah, pressure.
Okay, so
Let's see.
these. Volume
What you're
decreases,
getting
but the
is,
pressure
as you go
increases.
from here to here, the temperatures increase.
So these. So if this is what you're getting is, as you go from here to here, the temperature is increasing. Yeah, this one has to be bigger because these are both getting bigger.
So
Yeah,
it's-
this one
it's
has
a-
to be bigger
it's a
because these are
compression
both getting
heating.
bigger.
In fact, you get that type of
So it's-
effect
it's a-
on the
it's a
leading
compression
edge of
heating.
airplane wings.
When
In
they
fact,
go
you get that
really,
type
really
of
fast,
effect
like
on
supersonic.
the leading edge
get
of
compression
airplane
heating
wings
on the leading edge.
when they go
Not just
really, really
friction.
fast, like
It's
supersonic.
compression of the gas.
You get compression
So
heating
when
on the
the
leading edge.
SR-71
Not just
was
friction.
first built,
It's compression of
they
the
had
gas.
calculated, the engineers
So
had
when the
calculated that heat would be too
SR-71
high
was
for
first
aircraft
built,
aluminum.
They had calculated, the engineers
So
had
they
calculated
had to
that
go to
heat would be too
titanium.
high for aircraft aluminum. It would melt. So
Yeah,
they
the
had to go
wings
to
would melt.
titanium at those speeds. It would melt.
Yeah, the wings
Okay,
would melt.
so back to this
at
question.
those
D
speeds.
is a hydrocarbon and it's
Okay,
nonpolar. So
but
back to
it's
this
a
question.
big
D
molecule.
D is a
So the London
hydrocarbon
dispersion forces
and it's
are going to be
nonpolar,
big relative
but it's
to
a
some other
big
small
molecule.
molecule like nitrogen.
So the London dispersion forces are going to be big.
And then
relative
carbon
to
tetrachloride
some
is
other small
nonpolar,
molecule like nitrogen.
but it's also bigger than nitrogen.
And then
So
carbon
that means
tetrachloride
its,
is nonpolar.
viscosity
but
is
it's
going
also
to be
bigger
higher
than
than nitrogen.
Nitrogen is the best.
So that means
its
viscosity
has the
is going
lowest
to be higher
viscosity. Nitrogen is the best.
Yeah.
And actually, you can approach it
Has
that
the
way,
lowest
or the
viscosity.
other way you can approach it is.
Yeah.
Generally
actually,
speaking, you can approach it
liquids are
that
more
way,
viscous
or
than
the other way
gases.
you can approach it is.
So you can throw
Generally
everything out
speaking,
except for B.
liquids are more
and E.
viscous than gases. And
So you can throw
since
everything
E
out
is
except
polar,
for B and E.
you can throw it out and that leaves you with nitrogen. And since
That's
E is
two
polar,
approaches.
you can throw it out and that leaves you with nitrogen.
8.
That's two approaches. When a nonpolar
8.
liquid displays a convex meniscus.
So it's like this.
When a
in the
nonpolar
container.
liquid displays a convex meniscus,
So it's.
which
it's
of the
like
following
this
explains
in
this
the container.
behavior? It has a low surface tension and therefore clings to the glass. Which of the following explains this behavior?
Has a very
It
high
has a low
surface
surface tension and therefore clings to the glass.
The cohesive
Has a
forces
very high
holding it
surface tension.
together are stronger than the adhesive forces. The cohesive forces.
That's B.
Holding it together are stronger than
And
the
your
adhesive
example
forces.
is? That's B.
Mercury.
And your example is, in a glass tube, you see mercury with that type of
Mercury.
meniscus. Water, you see it the other way. In a glass tube, you see mercury with that type of meniscus. Water,
I
you
kinda
see
wish
it the
we had
other
a
way. Mercury barometer here.
They're fun to play
I
with.
kind of wish we had a mercury barometer here.
They're
Okay,
fun to
number
play
9.
with.
Which substance can be
Okay, number
described
9.
as cations bonded together by mobile
Which
electrons?
substance can
be described as cations bonded together?
Now we're talking
by
about
mobile electrons.
metals, metal elements.
Now we're talking about, so the only one that fits that
Metals.
is A. Silver is
Metal
the only
elements.
metal in that bunch. So the only one that
And
fits
that-
that is A. That is the
Silver is the only
electron
metal
C
in that
model bunch.
Remember that one?
And that, that is the electron C model.
See?
The electron C,
Remember that one?
SEA model.
What's the video one?
It was the electron
I don't know
C
if we saw a
SEA
video.
model.
What's the?
But we
video
did
one?
describe the two possibilities.
It was the electron C
I don't
model.
know
was
if we
the
saw a
earliest one.
video, but we did describe the two
And then
possibilities.
we
The electron
migrated
C
from
model
there
was
to
the
the
earliest
molecular orbital model. And then
Yeah,
we
I
migrated from there to the molecular
So
orbital
silver
model.
is the best one for 9.
Yeah, I do.
Yeah. So, silver is the best one for
Oh, yeah.
9.
Yes, one.
Dentist, oh, okay.
Are you healthy?
Oh, yeah, fine. Yes, one.
Dentist, oh, okay.
Which of the following, number 10, which of the following statements about steel is false? Which of the
Okay, so
following,
let's
number
see,
10,
A.
which of the following statements about steel is
it contains
false? Carbon atoms in the holes of
Okay,
its
so
iron
let's see,
crystals.
A.
Yeah. It
It's an
contains carbon atoms in the
interstitial
holes
alloy.
of its iron crystals. Yeah.
That's
It's
another
an
way of saying it.
interstitial alloy.
The presence of carbon iron bonds in the alloy makes steel
That's
harder and
another way of
stronger
saying
than
it.
pure iron. The presence of carbon iron
Yep, that's
bonds
true
in the
also.
alloy makes steel harder and stronger than pure iron. Pure iron is relatively soft
Yep,
and
that's
ductile
true
because
also.
it lacks directional bonding. Pure
Yeah.
iron is relatively
Yeah,
soft
when you
and
think of it
ductile
as
because it
a
lacks
molecular
directional
orbital
bonding.
situation.
Yeah, then you've got.
Yeah, when you think of it as
almost
a
an
molecular
infinite
orbital
gradation
situation,
then
energy
you've got
levels,
just almost
and those
an
electrons,
infinite
those outer
gradation
electrons
of,
are just free to move.
energy levels.
And
those electrons, those
nuclei
outer electrons are just
are
free to move.
really
not held in place.
And
They can shift around.
nuclei
So C is also
really
true.
not held in place. They can shift around. About D, the amount of carbon directly
So C
affects
is
the
also
properties
true.
of steel. Definitely. About D, the amount of
So all
carbon
of them are
directly
true.
affects the properties of steel. Definitely.
So all of them are true.
Let's see, 11. Which of the following statements is true about P-type silicon? Let's see, 11. Which
So
of
if
the
you
following
got
statements is
silicon
true about
In
P-type
your
silicon?
matrix, and you want a
P-type.
So
That
if you
means you
got
want to bond it,
silicon
you want to
in your
dope the
matrix,
silicon
and you want a
with something
P-type,
that has
that means you
one
want to
less
bond it,
electron.
you want a
positive
positive
the
type.
silicon.
So you
with
need to go
something that
one
has
less electron.
one
That
less
means
electron to the left of silicon
positive
in the
type.
table.
So
you
you
could
need
use
to go
boron,
one less electron.
aluminum,
That means
gallium to the left of silicon in
any
the
of those.
table. To the left of
You could
silicon.
use boron
has one
aluminum,
less gallium
or one
any of those.
fewer
It's to the left of silicon
valence electron.
has one less.
So let's see which one
or
satisfies.
one fewer
Valence
let's see.
electron.
It is produced by doping silicon.
So let's
with
see which one
phosphorus
satisfies.
arsenic. That's the wrong direction. Let's see.
It is
Protons are the
produced by
mobile
doping
charge
silicon
carriers.
with phosphorus
No,
arsenic.
protons
That's the
don't
wrong
move.
direction.
Yeah.
Only the
Protons are the
electrons
mobile
move.
charge carriers.
It does not conduct
No,
electricity
protons
as
don't
well as
move.
pure silicon.
Yeah.
Only
No,
the
it does
electrons
better.
move.
It does not conduct
Anytime
electricity
you've
as
got
well as
an
pure silicon.
imbalance, either positive
No,
or
it
negative.
does better.
It conducts electricity
Yeah.
more
Anytime
efficiently
you've
than
got an
silicon does.
imbalance, either
Pure
positive
silicon.
or negative.
So
it conducts
none of them are
electricity more efficiently than silicon
They're all
does.
false.
Pure silicon. So none of them
That's
are
why they
true.
call them semiconductors. They're all false.
They're not pure conductors like copper wire or.
That's why they call them
aluminum cables,
semiconductors.
high tension wires. They're not pure conductors like copper
They're
wire or
semiconductors.
aluminum cables and high tension
they're
wires. Semi for a reason because we can
they're
control
semiconductors.
the conduction. And they're semi for a reason because we can control. The only way to control a conductor
conduction.
is on or off. 14. The only way to control a conductor is on or off. A solid
14.
crystal of sodium chloride. A solid
All right.
crystal of sodium
Is
chloride.
what?
Well, let's take the first one. Looks like there's a list
All
in
right.
each one. Is what? So soft or
Well,
hard? Let's take the first one. Looks like there's
It's
a
hard.
list.
So
in
it's
each
either
one.
B or D.
So soft or
Okay.
hard? High melting. Both
It's
of them are
hard.
high
So
melting.
it's either B or
a
D.
good electrical conductor
Okay.
or
High
D,
melting,
a poor electrical conductor. Both of them are high melting. A good electrical
it's poor.
conductor or D, a
You
poor
have to have
electrical
mobile
conductor.
ions to conduct electricity. And a
it's
solid
poor.
crystal has everything locked in
You have to have
place.
mobile
They can't
ions to
move.
conduct electricity.
So
And a solid crystal
any
has
type of
everything locked in
solid
place.
salt like
They
that
can't
is, so
Not just table
any
salt, but
type
any
of
kind of salt.
solid salt like that
Is
is
a poor conductor. Not just
You
table
either have
salt,
to
but
put
any
it in
kind of salt.
solution
Is
or melt
a
it.
poor conductor. To get those ions
You either have to
loose.
put it in solution or melt it.
To get those ions
Okay,
loose.
15.
Which of the following has the
Okay,
highest
15.
melting temperature?
Okay.
Which of the following has the highest melting temperature? The highest melting temperature is one that has the strongest
Okay.
intermolecular forces available. The highest melting temperature is one that has the
water
strongest intermolecular forces
relatively
available.
low melting temperature.
Right.
0 degrees.
Water
Carbon
has
dioxide even lower than that. It's
relatively low
-78.
melting temperature. Right.
0
78
degrees.
and a half. Carbon dioxide
It'll
even
go
lower than
straight
that. It's
at
minus
78 and a half.
78.
It'll go straight from
78
solid
and
to
a half.
gas. It'll go straight
S8,
at 78 and a half.
which is
It'll go
sulfur.
straight from
That's
solid to gas.
A molecular compound. So
S8,
the attractions
which is
between
sulfur.
S8 and
That's
the
a-
other S8
a molecular compound
are,
are,
the attractions between S8 and the other S8 London dispersion forces are, because all those S's, London dispersion forces, are covalently bound. All those S's, P4 similarly, covalently bound. Magnesium fluoride would have the
P4
highest
similarly.
melting point of each one of those.
MgF2.
This is an ionic
Magnesium
solid.
fluoride
Has a
would
very
have
high
the
melting.
highest melting point of each one of those.
This is an ionic
Not the
solid.
highest, but
Has a
high.
very high melting point. Of that group, it's the highest. Not the highest, but
So
high.
D would be for 15.
Of that group, it's the highest.
16. So D would be for 15.
Which
16.
of these statements is false? Diamond is a covalent crystal. Which of these statements is false?
Yeah, it's- in
Diamond
fact,
is a
it's like a
covalent
single
crystal.
molecule.
As long as there are no
Yeah.
flaws, all
Yeah,
those
it's-
carbon
in fact,
atoms
it's
are
like a single
covalently bound to
molecule
each other. As long
in
as there are
that
no
single
flaws,
diamond crystal.
all those carbon atoms are covalently
B,
bound
the
to each
size of
other
the unit
in that
cell
single
of lithium
diamond
and
crystal.
cesium is the same. B, the size of
I
the
don't
unit
think so.
cell of lithium and
Because you
cesium is the
see where
same.
they're located. Lithium's way up here, cesium's
I
down
don't
here.
think so.
Because you see
The
where they're
size of the
located.
atom will
Lithium's way up
determine the
here,
size of the
cesium's
crystal.
down here.
And we can, the size of the
can
atom will
take the
determine the
radius of
size of
each
each one of
crystal.
these and calculate
And we
the
can-
volume for that unit
We can take the
cell.
radius
As long as
of
they're
each
the
one of
same
these
unit cell. And calculate the volume
So
for that
cesium
unit
would be the
cell.
bigger one.
As long as they're the same unit cell. So that one's false.
Right. So cesium would be
that's
the
the one
bigger
we're
one.
looking for, right? The false one.
So that one's
Okay.
false. None of the statements is false.
Oh, that's the one we were looking
so
for, right? We found
the
our
false
answer. It's B.
Okay. None of the statements is false.
E, so we
17.
found our answer. It's B. How would you
17.
expect the melting point of carbon tetrachloride to compare with sodium chloride? How would you
Carbon
expect the melting point
tetrachloride
of carbon
melting
tetrachloride
point
to compare with sodium chloride?
Compared to
Sodium
Carbon-
chloride, tetrachloride, melting point.
Well, first of all,
compared to
It should be less.
the
Sodium
melting point
chloride.
of carbon tetrachloride should be much, much less.
Well,
than
first
sodium
of all,
chloride. It should be less.
but
The
I
melting
suspect
point
there's
of
a
carbon
reason in
tetrachloride
there.
should be
it
much,
should
much
be
less
lower
than
because sodium chloride forms an extended
But
ionic
I
crystal
suspect
lattice,
there's a
whereas
reason in there.
carbon
It should
tetrachloride
be
is
lower
covalently
because
bound
sodium
small
chloride
molecule. forms an extended ionic
Okay,
crystal
that
lattice,
works.
whereas carbon tetrachloride is covalently
Are there any
bound
others
small
that might be
molecule.
better? It should be similar.
Okay,
No, it's
that
not similar.
works.
Should be
are there any
higher.
others that
Nope,
might be
not
better?
higher.
Should
Should
be
be
similar.
higher. Nope, no, it's
That's
similar.
D. C and D are bad. Should be higher.
Nope, not
They got
higher.
it
Should
flipped.
be higher. Nope, that's D. C
It's
and
not
D are
possible
bad.
to say anything about their melt. Oh,
Because
yes,
they're-
it is.
They got it flipped.
We found our answer. It's not possible to
A.
say anything about their melt.
Oh, yes, it is.
I mean,
We found
even
our
if I
answer.
got the key there saying it's A,
It's
I mean,
A.
Has to make sense too.
I mean, even if I got the key there saying it's
19.
A, I mean, it
Has to make sense too.
at normal
19.
atmospheric pressure and a temperature of 0 degrees C, which phase of water can
At normal
exist? Atmospheric pressure and a temperature of 0
At 1
degrees C, which
atmosphere.
phase of water can
And
exist?
0 degrees C.
At
What
one
phases of
atmosphere
water
can exist.
And 0 degrees C.
What phases of water can exist?
Uh-huh,
Zero degrees C?
uh-huh. If it's at the freezing point or melting point,
Not liquid.
right.
Well,
If it's at the freezing point or melting point, remember that diagram?
well,
That step chart where we had
Remember
the
that
heating over
diagram?
here,
boiling
that
is
step
no.
chart and temperature
Where we
was
had
up
the
here.
heating
We
over
start down
here.
here at minus
Boiling
20
is
for
no.
ice.
And it go up
And
here until you
temperature
got
was
to
up
0.
here. And then
We'd
we
start
started down
do?
here at minus 20 for
It would stay
ice.
there.
And it go up here until you got to 0.
And what
And then what
phases
would
were
it do?
present at that time? It would stay there.
Down here it's just solid
And what
up here
phases
it's
were
solid.
present at that time?
and liquid. Down here it's just solid
And until
Up here
all
it's
the solid
solid.
is gone,
and liquid.
then it won't increase in
And
temperature.
until all the
So
solid
as
is
long as you're
gone,
at 0 degrees, you've got
then
solid
it
and
won't
liquid at
increase
the
in
same
temperature.
time.
So as long as you're at 0 degrees,
It's counterintuitive.
You've got solid and liquid
But
at the
it's
same
true.
time.
So ice
It's counterintuitive,
and water, A,
but it's true.
both exist at the
So
same time.
ice
when you're at 0 degrees,
And water,
See.
A, both exist at the same time when you're at
0 degrees.
See.
Which of the following processes 20.
Which of the following
must
processes
exist in equilibrium with the evaporation process when a measurement of vapor pressure is. Must exist
is
in
made.
equilibrium with the evaporation
Okay.
process when a measurement of vapor pressure
Evaporation is one.
is made. Okay,
So evaporation is this one. So what's the other one? That is in
equilibrium.
evaporation is this way.
remember what it's called?
So what's the other one? That is in equilibrium with it.
Remember what it's called? Condensation.
So that would be E.
Okay, condensation.
So that would be E.
Okay,
All right. 21. I need a new marker. All right. 21. I need a new marker. You're given the following boiling point data. Which one of the liquids would you expect to have the
You're
highest
given the following
vapor
boiling
pressure
point
at room
data.
temperature? Which one of the liquids would you expect to have the highest vapor
Okay.
pressure?
How is the
at
vapor
room
pressure
temperature?
determined? Okay,
How is the vapor pressure determined? If you get a higher vapor pressure for this compound versus this compound,
What's happening?
if you get a higher vapor
22.
pressure for this compound
The
versus
intermolecular
this forces
compound,
holding
what's
this one
happening
together
are
between
lower.
the two. So
The
the vapor
intermolecular
pressure
forces holding
increases
this one
as the
together
forces decrease.
are lower.
So we need something with the
so the
lowest
vapor pressure
force.
increases as the forces decrease.
That's the one that's inverse. So we need something with the lowest force.
So they're
So which of the
Yes,
following liquids
that's
we
the one
expect to have
that's
the highest
inverse.
vapor pressure, the one with the lowest boiling point? So which of the following liquids we expect to have the highest vapor
diethyl ether.
pressure, the one with
Yeah.
the lowest boiling point?
Diethyl ether.
Diethyl ether. Yeah, diethyl ether. 22. 22. Which one of the following decreases as the strength of the attractive forces increase? Well, we just said that. Which one of the following decreases as the strength of the attractive forces increase? Well,
okay.
we just said that. Yeah, vapor pressure. That's the one that's opposite, goes
okay.
opposite from the forces. Yeah, vapor
E,
pressure.
vapor pressure.
That's the one that's opposite, goes opposite from the forces.
E, vapor pressure.
23. In which of the following processes will the energy be evolved as heat?
Energy.
23. In which of the following processes will the
evolved
energy
as
be
heat.
evolved as heat?
23. Energy.
So we have the different
Be
phases
evolved
here.
as
Let's say
heat.
we have gas up here.
23.
We have liquid over here.
So we have the
solid
different
over
phases
here. Let's say we have gas up
If we
here.
go from
We have liquid over here.
solid to
solid
liquid,
over here. That's melting, right? If we go from solid to liquid,
If we go
that's
from liquid
melting,
to solid,
right? That's freezing. If we go from liquid to solid,
If
if
we
we
go
go from liquid to gas, that's evaporation. If we go from liquid to gas,
and if we go from gas to liquid, that's condensation.
that's evaporation.
And if we go from
And if we
gas to
go
liquid,
from,
that's
let's see,
condensation.
like that. If we go from
And if
gas
we
to
go
solid,
from,
that's
let's see,
deposition, like that. If we go from gas to
If we go
solid,
from
that's
solid to
deposition.
gas, that's sublimation.
If we go from solid to gas, that's sublimation. Now, if we go from gas to liquid,
We're
now,
giving up energy.
if we
right?
go from
we're releasing
gas
energy.
to liquid,
So we're
this is
giving up
exothermic.
energy, right?
delta H is
We're
negative.
releasing energy.
That means this one would be
So
delta
this is
H.
exothermic.
Delta H is negative. That means
If we
this
go
one
from
would be
liquid
delta
to solid,
H.
with freezing,
Positive.
we're also giving up energy.
If we go from liquid to solid,
So
this one will be a negative
freezing,
delta H. We're also
giving
in
up
the
energy.
opposite direction will be a positive. So this one will be a negative delta H. And if we're going
In
solid
the
to
opposite
gas,
direction
will be a positive. We're absorbing. And if we're going solid to gas, we're absorbing.
Yeah.
We have to absorb energy. Let's see.
One point to the next.
Yeah, we have to absorb
Always.
energy.
One
Uh-uh.
point to the next. is
No, it can
always.
give up energy too.
What's the law that you change?
No, it can give up energy too.
What's the law says that you change forms that you're losing usable energy? One law says that you change forms that you're losing usable energy.
I don't know that one.
Wonder my all
I don't know that one. If it's in biology?
You lose usable energy whenever you change.
If it's in biology? Oh, yeah, I understand.
That was the same for everything.
No, if you're, yeah, I understand. If you're a heterotroph, or actually, if you're an autotroph, if you're taking energy in, if you're a heterotroph, or converting it and storing it, if you're taking energy in from a source, then it's not 100% converting it and storing it for use. In fact, as a general, it's not 100% efficient. You only store about 10% of the energy that comes in. In fact, as a general rule, or if you only store about 10% of the energy that comes in. You're only so from the sun about 10%, or the rest is waste. You eat a steak. Yeah, no, that's true. You're only getting about 10% of it. The rest is waste. Yeah, no, that's true.
Okay, so for, if we're going from solid to gas, we have to, okay, so for, if we're going from solid to gas, we have to.
We're going from gas to solid, we're giving up energy.
Positive, that's endothermic.
If we're going from gas to
now the
solid, we're
question
giving up
was,
energy.
That's.
Evolve as
Exothermic.
heat. So
Okay,
now the
any of these
question was,
negatives should be right.
evolve
Condensation,
as
deposition,
or
so
freezing,
any of these negatives should be right.
Let's
Condensation, deposition.
or freezing. Oh, there's one that I didn't mention, crystallization. Oh, there's one that I didn't
Okay.
mention, crystallization.
This is just phase change.
Crystallization can happen
Okay.
as a chemical process.
This is just
too.
phase change.
Crystallization can
But
happen
when you crystallize,
as
you're
a
going
chemical
from,
process too. Disperse to more
But
ordered,
when you crystallize,
and
you're
that
going
gives up
from,
energy. Disperse to more ordered. Sublimation, and
No,
that
that's
gives up
positive.
energy. Vaporization. Sublimation.
no, that's positive.
Vaporization. Vaporization.
Here it is.
That's positive.
Vaporization.
Melting.
Here it is. That's
That's
positive.
positive. Right. So crystallization, yeah, that works.
That's positive.
If you become more ordered, crystallization, yeah, does. That works. Then if you become more ordered, which is what crystallization does, then you give up energy. Okay, we got a phase diagram here that we're going to try to interpret. Okay, we got a phase diagram here that we're going to try to interpret.
Let me see, how much time do I have left?
Coming up on 2.
Let me see, how much time do I have left?
I gotta go. Coming up on 2. 3 o'clock is when we're supposed to start the lab.
So I got an hour left.
I gotta go.
A little over an hour.
3 o'clock is when we're
Okay,
supposed to
choose
start
the
the
correct
lab.
statement
So I
about
got
the
an hour
diagram.
left.
A little over an hour.
This is a phase diagram.
Okay, choose the correct
So
statement
we know
about the
where
diagram.
one atmosphere is located. This is a phase
25.
diagram. So we know where one atmosphere is located right here.
25.
One atmosphere is located. The diagram is
here.
qualitatively correct for water. Is that
There.
true? The diagram is qualitatively correct for
No.
water. Is that true? No, look at this no, the phase transition between solid and liquid. Phase. That line right there should have a negative slope. The phase transition
should go
between
up here
solid
like
and
that.
liquid. That line right there
So it's
should
not
have a
water.
negative slope. The diagram
go up
shows
here
that
like
the
that.
melting point of the solid increases
So it's
with
not
increasing
water.
pressure. The diagram shows that the melting point of the solid increases with increasing pressure. So the
Yes.
melting point is from solid. The melting
to
point is
liquid,
increasing toward the right as we increase
Yes.
the pressure.
That's
So,
true. B is true.
The melting point is increasing
None
toward
of
the
the above
right
is
as
correct?
we increase
Okay, so
the
we found
pressure.
our answer.
That's true. B is true. None of the above is
Okay,
correct.
we got another one
So we
here.
found our answer.
26.
Okay, we got another one here.
26.
Okay, below is a phase diagram for compound Q. You wish to purify a sample of
below is a
Q that
phase
was
diagram
collected
for
at
compound Q.
1 atmosphere pressure and 100
You wish to
purify a sample of Q
by
that was
subliming.
collected at
So
1
if we
atmosphere
collected
pressure and
it
100 K.
at 1 atmosphere
By
pressure, so that would be
subliming.
right here.
So if we collected
And
it
then
100 K,
at
it
1
would be
atmosphere
right here.
pressure,
So
so
right
that
in
would
this
be right
region
here.
right here is where we collected
And then
it.
100 K would be right here. So right in this region right
Now we
here
want to sublime
is
it
where we
to
collected
purify
it.
it. That is, we want to go from solid
Now
to
we want to
gas.
sublime it to purify it.
Right, so
That
remember
is, we
where
want to
everything's
go
located.
from solid
This
to
region here
gas.
is, right, so remember where everything's located.
solid.
This region here.
This region is liquid.
This region is gas.
So we want to go from
solid.
solid to gas.
This
right?
region is liquid. This
By
region is
subliming.
gas.
We want to go from
So
here
we want to go from solid
down
to
here
gas,
somewhere.
right? Right. How would we do
By
that?
subliming.
We want to go from here
Well, let's see. What are our choices?
to down here somewhere.
Right, how would we do that?
From the point that we started, if we
Well, let's
increase
see,
the
what are our
pressure to
choices?
1.5 atmospheres, then increase the temperature to
From the
300.
point that we started, if we
That would
increase the
go
pressure to
from
1.5
solid to
atmospheres,
then increase the temperature to
won't do it.
300. That would go
So A
from
can't be
solid
it.
to liquid. Increase the temperature to
That won't do it.
300K. So from 1 atmosphere here,
So A can't
we
be
go
it.
across to 300K. Increase the
K.
temperature to 300K.
That puts
So
us
from
right on
1
that line,
atmosphere here,
actually.
we go across to 300K.
And keep the pressure
at 1.
That puts us right
That
on that
won't do it.
line, actually.
And keep the pressure at 1. C,
That
lower
won't
the
do it.
pressure to 0.5. So we're starting here and we're going to go
C,
down to here.
lower the pressure to
0.5, right
0.5.
So we're
Lower the
starting
pressure,
here and then
we're gonna go
increase the
down to
temperature
here,
to 0.5 right here. So we go
Lower the
across this
pressure,
boundary
and then
between
increase the
solid
temperature
and
to
gas.
200. That will do it.
So we go across this
That will
boundary
sublime it.
between solid and gas. That will do it. So C is the
That will
answer.
sublime it.
So C is the answer.
Here's another one.
29.
Here's another one.
29.
Given the phase diagram below, which of the following statements is false?
All right.
Given the phase
solid-
diagram below,
let's see.
which of the following statements
None of the above is false. So
So
if we find a false
All
one,
right.
then the solid,
we
let's
can
see.
stop.
None of the above is false.
All right.
So if
Notice
we find
that
a
we've got
false
this
one, then
negative slope.
we can
So
stop.
we're probably dealing with water. All right. Notice that we've
The
got
solid
this
has a higher
negative
density than the
slope.
liquid.
So we're probably dealing with
So
water.
the solid's here.
The solid has
and
a
the
higher
liquid's
density
here.
than the liquid. So the solid's here.
Solid and the
That's
liquid's
false.
here. Right. Right. We know that for water, the solid is a lower
Solid,
density
that's
than the
false.
liquid. Right. Yeah. Right. We know that
So
for
the key
water,
there
the
is to
solid
recognize that
is
this
a
is
lower
probably
density
water.
than the liquid.
And then you know that
Yeah.
water solid
So
density
the key there
less
is to
than
recognize that this is
liquid
probably
density.
water.
And then you know that
Okay.
water solid
Yeah.
density is less than.
So
See
A,
a negative,
liquid density.
if you see a negative slope line like that, that's typically water.
Yeah.
Period.
Yeah.
So
See
A,
a negative.
I
if you
don't,
see
I
a
don't,
negative
in
slope
fact, I've
line
never
like
seen
that,
any
it's
other
typically
that
water.
was,
So
Yeah.
any other simple phase
I
diagram.
don't,
In fact, I've never
that
seen
was
any
anything
other
other
that
than
was,
water with that negative slope.
any other simple phase
Now, they-
diagram.
Some of these phase
that was
diagrams
anything
can be
other than
really
water with that
complicated.
negative slope.
Right.
If you were going
Now,
into engineering,
some of
they'd
these
be
phase
exposed
diagrams
to
can
that,
be
but-
really complicated. Right.
If you were
Fortunately,
going
we're
into
not.
engineering.
Okay, now
they
we're
would
getting a
be
little more
exposed to
difficult
that.
questions.
we're changing.
Fortunately, we're not.
Okay, now
We're
we're
getting a little
still,
more difficult questions.
we're still chapter 10, but now we're moderate. We're still chapter 10,
So,
but now we're moderate.
I guess I'm gonna have to identify
So-
moderate questions too, because they're
I guess I'm gonna
renumbered.
have to moderate number one.
Identify moderate questions too, because they're renumbered.
Which of the following is the correct
Moderate
order of
number
boiling
one.
points for KNO3, CH3OH,
Which of the following is the correct
order of boiling points for KNO3,
Well, the boiling points are gonna decrease.
C2H6, and neon?
Let's see.
Well, the boiling points are going to decrease. The boiling points should decrease in that order.
Let's see.
From potassium
Yes.
nitrate.
The boiling
through
points should decrease
methanol,
in that order.
through
Ethane.
From potassium
neon.
nitrate.
The
through
boiling points should
methanol,
decrease
through ethane.
through neon. The
So,
boiling points
let's see,
should
which defines
decrease.
correct order?
Boiling points.
So
They're saying they're
let's see,
increasing.
which
So
defines
we
correct
just
order?
flip those around.
Start with neon.
They're
go to
saying they're
ethane,
increasing.
go to
So we just
methanol,
flip
and
those
then go to
around.
Start
Potassium
with
nitrate.
neon. Go
And
to
D fits
ethane,
that
go to methanol, and then go
So
to
the lowest boiling
potassium
point is
nitrate.
neon.
And D fits that one.
We just flipped it around.
So the lowest boiling point is neon. Yeah, the highest boiling
We just
point is
flipped
going
it
to be
around.
potassium nitrate. But lowest boiling point is going to be neon.
Yeah,
The highest boiling point
Next
is going
is
to be
ethane
potassium
and then
nitrate. Lowest
methanol.
boiling point is going to be neon.
Next
Because
is
of the
ethane
types
and
of
then
forces that are available.
methanol.
Ionic forces for potassium nitrate, because of the types of forces that are
hydrogen
available.
bonding for
Ionic forces
CH3OH.
for potassium nitrate, and
then
then hydrogen
battle
bonding
here's
between
for
neon
CH3OH.
and ethane, and their
London
and then
dispersion forces.
battle here is
And the
between
small
neon and
atom of
ethane,
neon
and their
has the very
London
lowest
dispersion
London
forces.
dispersions.
And the small atom of neon has the very lowest London
All right.
dispersions.
Number 4 for the moderates.
All right.
Number
Might
4
have to
for the
work this one
moderates.
out. Assume 1,250 joules of energy is added to 2 moles
We might have to work this one
of
out.
water. Assume
as an ice
1,250
sample
joules of energy
at
is
0
added
degrees.
to 2 moles.
The molar heat of
Of
fusion
water
is 6.02
as an ice
kilojoules per
sample
mole
at 0
Specific
degrees.
heat of liquid water
The
is
molar heat of
4.18.
fusion is
The molar
6.02
heat of
kilojoules per
vaporization
mole.
is 40.6.
Specific heat of liquid
The
water is
resulting sample
4.18.
contains which of the following?
Molar heat
All
of
right.
vaporization is 40.6.
So I find it the best
The
is
resulting
to
sample contains which
do
of the
this one
following?
is to
All right.
draw yourself a diagram. So I find it the best
And
is
you're going here from.
do this one is to
This is
draw yourself
heating
a
solid.
diagram. Then solid liquid.
And you're going
And
here
then
from
liquid
this is
heating.
heating the solid,
And then liquid
then solid,
solid.
liquid,
And then
so
liquid gas.
heating, and then gas.
And then
So
liquid
this is the
solid.
gas, and then
This is liquid.
liquid gas, and then gas.
So this is
This
the
is
gas.
liquid only.
This is liquid to.
And this is solid to
This is
liquid,
liquid only.
and this is solid,
And this is solid.
So we're starting
liquid.
off, we have
And this is solid
1,200
only.
joules of energy that's being added. So
Two moles.
we're starting off,
36
we have
grams.
1,200
So we've got a
joules of
mass
energy that's
of
being added. 2 moles.
36 grams.
36 grams.
Of water. So we've got a mass
two
of
moles.
36 grams
Of
of water or
Yeah,
2
water.
moles. So the number of
Of
moles is
Water,
that,
for water, yeah.
water.
So when we start
So the number of
off
moles is
at,
that,
for water.
0 degrees.
So
this
when we
is gonna be
start
0
off
degrees right here,
at
right?
0 degrees, we're starting to melt.
So this is
We're not
gonna be
heating
0
up
degrees
the
right here.
ice. We're only melting
Right,
the
we're
water. We're starting to melt.
So
We're
how
not
much
heating
energy
up
is
the
it gonna
ice.
take
We're only
to melt
melting the water.
36 grams
So
of
how much
water
energy is it going to take
at 0 degrees?
to melt
36 grams of water.
specific heat
Let's
at
see,
0 degrees? The molar heat of fusion. That's how
let's
much
see,
energy it takes to melt
the molar heat of fusion.
a mole of water.
That's how much energy it
So
takes.
the amount of energy
to
here
melt
a mole
right,
of water
is going to be
So the
6.02.
amount of
energy here 6.02
is going to be
kilojoules
6.02
per mole times how many moles? 6.02 kilojoules, right? Per mole times how many moles?
of water.
2 moles, right?
Okay.
So that's 12.04
water.
kilojoules. Okay.
We're
that's
given joules.
12.04, so
That's equal
kilojoules to
We're given joules.
12,040. So that's equal
12,040
to joules.
Just to melt the water.
12,040. 12,040.
Okay.
So we
Joules.
started off with 12.
Just to melt the water.
12,500.
Okay.
So we started off with 12,500. That's what we started off with. Now we've used up 12,040. That's what we started off with. 0. Now we've used up 460 joules left over. That's 0.
That's going to be used
6
to heat the liquid
460
water.
joules left over.
Okay. That's going to
So,
be used to
the
heat
amount
the
of
liquid
heat
water.
That's
Okay.
going to be used for the liquid water is specifically the amount of heat
We did this one.
that's going to be used
Last
for the
time,
liquid
right?
water is
Or did
specifically
we do
the
this
water.
first semester? We did this one last calorimetry. We did it first semester.
Or did we do
Yeah,
this first semester?
first semester.
Times mass times change in temperature.
Calorimetry. We did it first semester.
Yeah.
So specific heat of water is
Times mass
4.18
times
joules.
change in temperature. 4.18
So
joules
specific heat of
per
water is
gram degree
4.18
C.
joules.
Times mass, which is
4.18
36
joules
grams per gram degree C.
Times
Times
mass,
change in
which is
temperature.
36 grams.
Right, so initial temperature is 0, times change in
final
temperature minus initial. So initial temperature is 0 minus initial. So final temperature is minus initial, delta H, which
Minus
is
initial.
equal to 460 joules is, okay, delta H,
So we got
which
this
is
one
equal
unknown
to
here.
460 joules. Final temperature minus, 0, which
So we
final
got this one
temperature?
unknown here. So 4.18 times 36.
Final temperature minus, 0, which
is-
final temperature? This one
So
right here
4.18 times 36.
is this one right here. So that's 150 point. So that's 150, and that would be joules per degree C. And then if we keep
And
this
that
one
would be
on
joules
this side per degree C, then we divide 460. And then if we keep this one
divided
by
on this side,
150.5, then we divide 460. And that's equal to the temperature of the water
divided by 1
after we've used up all
the rest of the
five,
heat.
and that's equal to the
Assuming
temperature of the water
We did
after we've
use
used
up
up all the rest of the heat. If the temperature
Assuming
exceeds 100 degrees, then we know
we
that
did
we
use
didn't
it
use
up.
it all up. If the temperature exceeds
so
100 degrees, then we know that we didn't use it all up. 0.5, yeah. Sorry. So
460 divided by 150.
460.
0.5,
It's just inverse that.
Sorry.
Divide.
Yeah.
So I got
460, that's just
3.1
inverse that,
degrees.
divide.
So I got
So it's gone from
0 to 3.1 degrees.
3.1 degrees. I think it's still liquid. So it's gone from
It's all
0
liquid. To
Only
3.1
water.
degrees.
I think it's still liquid. It's all liquid.
Okay. Only water.
That's one of those problems that,
Okay.
when it first hits you, you say, oh my God. That's one of those problems that,
No.
right, when it
And
first
then you have to
hits you,
sit
you
and
say,
break it down.
oh my God.
That's
That's
where
where
drawing
drawing
a
a picture helps.
No.
And then you have to
Shows
sit
you
and
what
what
steps
steps
are
are actually going to
That's where
proceed.
drawing a
as
picture
you use
up the heat.
Shows you what steps are actually going to proceed.
As you use up the heat. All right, let's see, what's next? Chapter 10, difficult. Let's see, what's next?
So we're renumbering this. Got all this yet?
Chapter 10,
Difficult. So we're renumbering this. Got all this yet?
My 101 class in Beckley was complaining because my 101 class.
I was describing stoichiometry. We had a balanced
Complaining
equation.
because
We
I
were
was-
doing
I was describing
calculations.
stoichiometry.
And I would do a calculation here and then go over
equation,
here and then I go back over here.
You're all over the
And
place.
I would do a calculation here
Can't
and then
follow
go
you.
over here and then I go back over here.
So you're all over the place.
I need to try to be more ordered.
Can't follow you.
I need to try to be
Difficult.
more ordered.
Okay. A crystal was analyzed with X-rays
Difficult.
having 2.33
Okay.
angstrom wavelength. A crystal was analyzed with
firing
X-rays
having
at a crystal 2.33 angstrom
with-
wavelength, and the X-rays are
So we're
2.33
firing
X-rays
angstroms
at a
in
crystal.
wavelength.
Right, what's an angstrom?
With-
With, and the X-rays are 2.33
Angstrom.
angstroms in wavelength.
One angstrom
Right, what's an
is
angstrom?
10 to the
Remember what an
minus
angstrom
10th angstrom.
Meters.
One angstrom is 10 to the
Okay.
minus 10th meters.
So it'd be,
1 angstrom is a tenth of a nanometer.
so it'd be,
1
Okay.
angstrom is a tenth of a
so our
nanometer.
X-ray wavelength
Is 2.33.
So our
angstroms,
X-ray
correct?
wavelength,
Is
the angle of the
2.33
first order diffraction, where
angstroms,
n
correct?
equals 1.
N equals 1.
The angle
The
of the first
angle
order
of that
diffraction,
fraction.
where
We're
n
talking about the
equals
Bragg
1.
equation here.
N equals
It's
1.
19.2
The
degrees.
angle of that
Fraction. We're talking about the Bragg equation here. It's
What would be the angle for the
19.2
second
degrees.
order diffraction?
So if we say N equals 2,
What would be
We
the
still got
angle
the
for the
same
second
wavelength.
order diffraction?
so if we say
2.33
N equals 2,
angstroms.
we still got the same
Then
wavelength.
we want to know
2.33.
That one, angstroms.
Then we want to
Okay.
know,
So
What's
where's the
that
Bragg
one?
equation? I want to be sure and get
Okay.
it right. So
It should be in
where's the
useful
Bragg
information.
equation? I want to be sure and get it right.
Let's see.
It should be in useful
Bragg, here it
information.
is. N lambda 2D sine
Let's
theta.
see, Bragg, here it is.
N lambda 2D sine theta.
D sine lambda, 2D sine.
okay, there are two approaches to this. We've got N. Okay, there are
We've got
two
the
approaches to this.
wavelength. We've got
N.
We've got the
Angle.
wavelength.
We can calculate the distance
We've
between the
got,
layers, and that won't
the
change. Angle. We can calculate
Or-
the distance between
And
the
then we
layers.
can go and
And
then
that
plug
won't
it back
change.
in now and substitute 2 for N.
Or,
And then we can
Or
go,
we can
and then
say,
plug it
all right,
back in now and
this one
substitute
for
2
that
for
one
N.
has its parameters. This one for this
Or
one has
we
its
can say,
parameters.
all right,
Where do they meet?
this one for that one has its
Well, they meet with the
parameters.
same
This one
lambda.
for this one
and
has
has
its
its parameters. Where do they meet? Right. Well, they
So
meet
if we
with the
set
same
this
lambda
one
and the same
D,
distance is the same.
Right.
So if we set this one,
If we solve this
the
one for
distance
D,
is the same. D equals.
if we solve this one for
let's see.
D,
D
N
equals
lambda, let's see, over 2. N lambda over 2. Let's see, we divide by sine theta here, sine theta, there we go. Let's see, we divide by sine
There we
theta
go.
here.
So
Sine theta, there we
if
go.
the distance is the same for both of them,
There we
then,
go.
so if the distance is the same for both of them.
This is gonna be the same, this is
Then,
gonna be,
uh,
2's gonna be the same.
And theta is gonna be
This is gonna
different.
be the same.
So
This
the
is
two
gonna
things that are
be-
different are
2's gonna
sine
be the
theta
same.
and n. And theta is gonna be different.
So the two things that are different
So
are
if we-
sine theta.
If we
and
equate this and we say that and that and that.
So
if we equate this and we say
Then
that and
these are
that
gonna
and
cancel.
That. This is gonna
Then
cancel. And we're left with.
These are gonna cancel.
This is 1.
This is gonna
and
cancel.
This is.
And we're left with 19.2.
This is 1.
This is 2.
And this
Now that's our
is
unknown.
19.2. This is 2. And now that's our unknown.
Okay?
Yeah.
Okay.
Okay, delusion.
So let me clean it up. On this
Okay.
side, we have 1
After
So let me clean it up. On this side, we have
19.2 degrees.
over.
On this side, we have
Sine
2
of
divided by
19.2 degrees.
sine of theta. On this side, we have 2 divided by
Okay?
sine of
So if we
theta.
put this one by itself, we want sine
Okay?
theta on one side.
So if we put this
And
one
then we just
by
bring,
itself, we want sine.
let's see. This is in
theta
the
on one
denominator, be in
side.
the numerator over
And then we
here.
just bring,
Let's
2
see. This is in the
sine
denominator, be in the
19.2
numerator over
degrees.
here. 2 sine 19.2 degrees.
Okay, so what's the sine of 19.2
Yeah,
degrees?
divided by 1.
I hope I did this right.
Okay, so what's the
19.2.
sine of 19.2 degrees?
I hope I did this right.
That's
19.2.
0.3289.
Sine.
0.3.
So that's 0.3289.
Times 2. Now that's equal to
0.3289. 0.6578.
Now that's equal to
Is sine 0.6578.
Theta is the arc sine of this value.
Is
The
sine,
arc sine is
going the
theta.
other direction.
Now, theta is the arc sine of this
So let me
value.
find my arc sine.
The
Keith.
arc
Here it
sine
is.
is going the other direction.
And I get 41. So let me find my arc sine, Keith. Here it
0.1
is.
degrees,
And I get 41.
0.1
Is that
degrees.
jive? Yeah, 41.1. Had me worried there for a
Is
minute.
that
I
jive?
didn't know if I was coming out with Yeah, the right answer. 41.1. Had me worried there for a minute.
Now, that's the way I
didn't know
would
if I
do
was
it.
coming out with the right answer.
You can go ahead and use this
Now, that's the way I
information
would do it.
and calculate D. You can go ahead and use
Okay.
this information and calculate.
Then you can
D.
come back to this equation
and put D in, and your unknown is
Then
still
you can
theta.
come
back to this equation
and then solve for theta.
and put D in, and your unknown is still theta.
And then solve for theta.
All right, so that was, oh, I didn't put the right.
That was number
All
one.
right, so that was
I'm sorry?
Oh, I didn't put the right.
That was number
in
one.
the first equation, and then put D
I'm sorry?
into the second equation with the new
In the
n.
first equation.
The n, and then put D into the
This is the
second
order.
equation.
This is the,
With the new n. The n
fundamental.
now is 2, is n equal
This is the
1.
order. This is
And
the.
this is the
first
overtone.
fundamental.
I'd say in
is
terms
n
of
equal
music,
1.
be the first
And
overtone.
this is the
first overtone that you might say in terms of music, be the
That
first
has a
overtone.
different name in optics.
That has a different name. in,
Okay.
Yeah, optics.
Got it? All right. Okay. Got it? All right. But if you do it my way, then you don't have to worry about the units of measure. But if you do it my way, then you don't have to worry about the units of
I would
measure.
always be wondering,
Now, should I use angstroms or should I use nanometers?
I would always
or
be
what?
wondering.
Now, should I use angstroms or should I use nanometers
Okay.
or what?
Number 2, chromium metal crystallizes as a body-centered cubic lattice.
Okay.
Number 2, chromium metal crystallizes as a body-centered cubic lattice. Body-centered cubic, so you got chromium here, 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 there,
Body-centered
there,
cubic,
so you got there. Chromium
And you
here,
got
here,
one,
here, chromium in the
there,
middle. There.
That's
And
a
you got
body-centered
one
cubic.
Chromium in the
If the
middle.
atomic radius of chromium is 1.25. That's a
angstrom.
body-centered cubic.
R
If the
equals
atomic radius of chromium is
1.25
1.25 angstroms.
angstroms. R equals 1.25.
What's the density of chromium in grams per cubic
angstroms.
centimeter?
So we're looking for the density
What's the density of
chromium.
chromium in grams per cubic centimeter?
in grams
So we're looking
per
for the
cubic
density.
centimeter of chromium.
What do we need to know?
In grams
To calculate
per cubic
density.
centimeter. We need to know the mass.
What do we need to know to
in that
calculate
cube, and we
density?
need to know the volume in that. We need to know the mass in that cube,
So,
and we need to know
A
the volume in
body-centered
that
cubic
cube.
lattice. Let's see. I think that's Go to our useful
So,
information.
body-centered cubic lattice. Let's see. I think that's,
Go to our useful
it might be
information.
BCC. There it is. BCC edge equals, it might be BCC. There it is. BCC
What's
edge
that A
equals,
stand
what's that A stand for? It's 4R divided by the square root of 3. What's the A in there for? It's
Does yours have an A
4R
in it?
divided by the square root of 3. What's the A in there for?
Does yours have an A in it?
No. I don't know what that little A stands for. I think it was a typo. No. 4R
I don't know what that
divided by the
little A
square root of
stands for.
3. I think it was a typo. 4R divided by the square root of 3.
Let me check something. Let me check something.
Is the useful information the work problem?
Huh?
Is the useful information in the work problem?
No.
Huh?
No,
Is
it's in the,
useful information
the
work
printed-
problem?
it's in the
No.
printed, no, it's in the printed review document. Review document.
Oh, yeah. Oh, yeah. Thought I had it in one of these slides. Thought I had it in one of these slides. Oops. This is face-centered cube. Oops, square root of 8. This is face-centered cube. I thought I had another slide with
Square root of
those
8.
others in here also. I thought I had another slide with those others in here also. Well, I don't see it. Well, I don't see it.
Well, let's work it out with this formula and see.
What'd I say?
Well, let's work it out with this formula and see.
What'd I say?
Oh, wait a minute.
It's too difficult. You just look at the worked problem.
Oh, wait a minute.
That's what you
Too
were doing, wasn't
difficult.
it? You just look at the worked problem. Okay. That's what you were doing, wasn't it? It's 2. Okay. It's 2. What's wrong with this thing? Oh, that's chapter 11. What's wrong with this thing? Oh, that's chapter
Here we
11.
go.
Yeah, 4R.
There should be
Here
an
we go.
equal sign in there.
Yeah,
A equals.
4R.
There should be
Where?
an equal sign in there. A equals. Equals on the wrong side.
Where?
Yeah, it should be between A and the formula. Equals on the wrong side.
4R divided by the square root of
Yeah,
3.
it should be between A and
So
the
the edge on
formula.
this cube right here. 4R divided by the square root of 3. That distance. So the edge on this cube right here. Equals. That
4R
distance.
divided by the square root of 3
Yes.
equals,
There we go.
4R divided by the square root of 3.
So this is going to give us the edge on
There
that
we go.
cube.
Which is 4 times 1.25.
So this is going to give us the edge on that cube, which is
divided by the
4
square root
times
of
3.
1.25 angstroms. Divided by the square root of 3.
5 enter 4 times 3 square root divide 1.25.
Okay, this is
times 3 square
2.887
root divide.
angstroms.
Okay, this is
equals D.
2.887.
And
Why don't we just,
angstroms.
why don't we
equals
go
D.
ahead and convert angstroms to,
And
why don't we just,
centimeters first.
why don't we
before
go ahead and
cube it.
convert angstroms to
Okay.
centimeters
So-
first before we cube it? Okay, so let's do that. Well, I said angstroms is 10 to the minus 10th meters.
Well, I said angstrom, and then a meter, 10 to the minus 10 is 100 centimeters, right? Right. And then a meter is 100 centimeters, right?
So 2.887 times one exponent. So 2.887 times one exponent. Minus.
So I get 2.8889 actually. So I get 2.8 times 10 to the minus 889 actually, centimeters. 9 times 10 to the minus 8 equals 2.89 times 10 to the minus 8 equals centimeters. 2.89 times 10 to the minus 8.
I just cube this one.
Centimeters cubed.
So I just cube this one.
Yep. So this is 2.41 times 10 to the minus 23. This is 2.4 cubic centimeters. That's the area. 10 to the minus 23.
I mean the volume. That's the volume of the
Cubic
cube.
centimeters. That's the area.
So now what we need is the mass. I mean the volume. That's
Well,
the
in order
volume
to
of the
get the
cube.
mass,
So now what we need is the
chromium.
mass. We also need to know how many
Well,
atoms.
in order to
does
get
that
at the
represent?
mass, we need to know it's
Remember?
chromium.
We also
With
need to
these,
know how many atoms does that
1/8 of
represent.
these 8 corners is one, and then the
Remember?
one in the center is another.
With these,
So actually there are
1/8
of these 8 corners is
atoms,
and then the one in the center is another.
chromium.
So actually there are 2 atoms. We need to convert of chromium, that to moles of chromium, right? And we need to convert that to moles, because we have no useful, because we have no, in terms of grams for atoms. We have no useful,
Not readily available.
mass, so in terms of grams
convert these to
for
moles.
atoms. Now we can convert moles
Not readily
of
available.
chromium
So
to
we can-
grams. We can convert
we
these
just
to
need
moles, and now we
more
can
mass
convert moles of chromium to grams. We just need
More mass.
52.00. Which is 52.00.
Okay. So let's see. 252 times and divide by 6.022. So let's see. 252 times and
So
divide
that
by
is 1.73 times 10 to the minus 22 grams. So that is 1.7. Now the density times 10 to the minus 22 mass divided by volume. So now the density equals mass divided by volume. 2.41 times 10 minus 23. 2.4 centimeters times 10 minus 23
divide.
centimeters. 7.18.
I just need to flip these and divide.
I get
Grams per
7.18 centimeter. Grams per cubic centimeter. Here? That's the distance here.
Okay, yeah, that says length on it. That'd be.
Okay, yeah.
Now we can
That's
use
the
something
distance
that's
here.
Okay, yeah,
consistent.
that says length, BCC.
Okay, yeah.
Now we can use something that's consistent.
Body centered cube.
It says
Uh-huh.
length, BCC, I guess that means body.
So the answer is B.
Yeah,
After all
body
that
centered
trouble.
cube.
Uh-huh. So the answer is B.
7.18
After all that trouble.
grams per cubic centimeter. Density
That
is
wasn't too
7.18
disordered. I
Grams
mean, I
per
went
cubic
way over
centimeter.
here, then I went up here, and then I went up there.
That wasn't too disordered.
I mean, I went way over here,
I'm better.
then I went up here, and then I went up there.
All right, I agree. I'm better.
You still writing? Okay. All right, we're ready for chapter 11. You still writing? Okay. All right, we're ready for chapter 11 now.
Just leave me the top part, that's it.
Okay. Chapter
Just leave me the
11
top part, that's it.
and
Okay.
easy. Chapter 11 and easy. So I can go here and down there.
Yeah,
So I can go here and down there.
yeah. You can, that bottom part too.
Okay.
I'm just putting that last equation. You can, that bottom part too.
Okay.
I'm just putting that last equation.
And this is gonna be number 1.
So now we're
And
getting into
this is gonna be number
solutions.
1.
So now we're getting into solutions. In a 0.1 molar solution of sodium chloride in water, which one of the following will be closest to 0.1 molar solution of sodium chloride in water, which one of the following will be closest to 0.1?
Sodium chloride, 0.1 molar sodium chloride
All right.
in aqueous solution.
I'm trying to figure a way we can do this without having to calculate every one of them. I'm trying to figure a way we can do this without having to calculate every one of them.
Expression is 0.1 mole. This expression is 0.1 solution mole per liter of solution. 0.1 molal is 0.1 mole. 0.1 molal kilogram is 0.1 mole per kilogram. 1 liter of water is about 1 kilogram. Okay. 1 liter of water. And when you add a little bit, 0.1 mole of sodium chloride, you're not adding that. And when you add a little bit, so this one is going to be of sodium chloride, you're not adding actually just a little bit larger number. So this one is going to be actually just a little bit larger molal. It's going to be a little bit larger, but not actually. We take this one and convert it to molal. The molal, it's going to be a little bit larger, very close to each other. That's the mass fraction is going to be different. The mole fraction is going to be different. Very close to each other. The mass fraction is going to be different. They're not all 0.1. Different. Molality is the best. They're not all 0.1. Molality is the best. Any other way to reason it than that. Otherwise, we got to go any other way to reason it than that. And otherwise, we got to go ahead and calculate every one of them. Number 2, and I'm not up for that. Which of the following concentration measures will change in value as the temperature of a solution changes? Which of the following concentration measures will change mass percent in value as the temperature of a solution changes? Will it change? No. Mass percent? It won't change. Mole fraction? Will it change? No, it won't change either. It won't change. Okay, so mole fraction won't change. Mole fraction won't change. It won't change either. Okay, so percent won't change. Molality? Mole fraction won't change. It's based on mass. Molality, moles and mass. Molarity, it's based on mass. That's the one. Moles and mass based on volume. Molarity, that's the one. Because it's based on volume. Three. Which of the following chemical or physical changes is an endothermic process? 3. All right. Which of the following chemical or physical changes is an endothermic process? In order for the phase to change. Which one requires energy? A solid, in order for the phase to change. Endothermic. If you go from a solid to a gas, you gotta put energy into it. A solid, endothermic. If you go from a solid to a gas, you gotta put energy into it. Yeah, liquid to gas, you gotta put energy into it. Evaporation. Yeah, liquid to gas, you gotta put energy into it. There it is, yeah. Combustion of gas is exothermic. Oh, okay, there it is, yeah. Mixing of sulfuric acid and water is exothermic. We assume that's concentrated sulfuric acid. Mixing of sulfuric acid and water. That's why they say concentrated you ought to add acid to water. That's an endothermic process. Don't add water to acid. That's why they say do as you ought to add acid to water face. Don't add water to acid. Freezing of water, or that's the other way around. That's exothermic. It goes from a liquid to a solid. Freezing of water, up energy to do that. That's the other way around. That's exothermic. Okay, so A is the right answer. It goes from a liquid to a solid. It's giving up energy. Number 4. To do that. Okay, so A is the right answer. Number 4. Which statement about hydrogen bonding is true? Well, let's see. Which statement about hydrogen bonding is true? Hydrogen bonding is intermolecular attraction forces between 2 hydrogen atoms. Hydrogen bonding is intermolecular attraction forces hydrogen between 2 hydrogen atoms. Water molecule causes I don't think so. 1, 2, 3, 4. Hydrogen bonding capabilities water molecule more soluble in water than 1, 2, 3, 4 butane. To be more soluble in water than methanol is more soluble. No. Hydrogen bonding of a solvent molecule with a solute will not affect the solubility of the solute. Hydrogen bonding of a solvent molecule with a solute will not affect the solubility of the solute. That's why we say like dissolves like. Most definitely.
D, hydrogen
That's why we
bonding
say like
interactions
dissolves
between
like.
molecules are stronger than the covalent bonds within the molecule. D, hydrogen bonding interactions between molecules are
we know what
stronger
would
than the
happen if that were
covalent bonds
true.
within the molecules.
Right.
All the molecules get ripped apart.
Right, we know what would happen if that
So
were
the
true.
last one is our only choice.
Right.
Hydrogen
All the
bonding
molecules get
arises from
ripped
the
apart.
dipole moment created by
So the
unequal
last one is
sharing
our
of
only
electrons
choice.
within
Hydrogen
certain
bonding
covalent
arises
bonds
from
from
the
the
molecule.
dipole moment created by
That's the one.
unequal sharing of electrons within certain covalent bonds within a molecule.
Number 5, that's the one. Number 5,
Which of the following favors the solubility of an ionic solid in a liquid solid? Which of the following favors the solubility of an ionic solid? A large magnitude of
in a
solvation
liquid
energy
solid.
of the ions. Let's see, a large magnitude of solvation energy of the ions. Well, that's not the only thing.
large magnitude of solvation
That's
energy.
one of the things. That's not the only thing.
Right.
If we're looking at, delta H one,
That's one of the
delta
things.
H2,
Right.
and delta
If we're looking at,
3, delta H1,
this is
delta
the,
H2, and delta H.
solute,
3, this is the,
bond breaking,
solute,
right?
this is the solvent,
Bond breaking,
make a hole,
right?
this is the solvent, and this is
Make a hole.
the association. And this is
solute
the
and
association,
Of solute
and that gives you the overall solution heat. And that gives you the
These are
overall
both endothermic.
solution heat.
Exothermic, excuse me.
These are
Exothermic.
both
Endothermic, right?
You have to put energy in.
Exothermic, excuse me. I was right the first
Exothermic.
time.
Put energy
Right.
in,
You have to put energy in.
put
No,
energy
the
in,
endothermic, I was right the
get
first
energy
time.
back. Put energy in,
So
Put
a
energy
large
in,
magnitude of solvation
energy
energy
back.
of the ions. Solvation, this is
This
so
is the
a large
solvation
magnitude
energy
of
right here.
solvation energy of the ions. Solvation,
this
where they
is
combine.
the solvation energy right here.
Small magnitude of the lattice energy
Where
of the
they
solute.
combine.
All right.
Did we talk about this at
Small
all?
magnitude of the lattice energy of the
I
solute.
don't think so.
All right.
Did we talk about
Did we
this
talk
at
about it
all?
last semester?
I don't think so.
Lattice energy. Yeah, okay, so you know
Did we
what
talk
the
about it
term
last
means.
semester?
Lattice energy
Lattice
is
energy.
energy where.
Yeah, okay, so you know what the term means.
X as a gas, lattice energy is the
And
energy
Y
where
as the anion gas.
X as a gas come together and form
And
X,
Y
Y
as the
anion
solid.
gas.
And that gives up
Come
a lot of
together and
energy.
form X, Y
Extremely
solid.
exothermic.
That gives up a lot of energy.
It's extremely exothermic.
So a small
okay.
magnitude of lattice energy of the solute. So a small magnitude of lattice energy
would
of the
be
solute.
large would be negative, but the
Lattice energy would be
if it's a small
large would
value,
be
be
But it
negative.
doesn't take much energy to break it
But
apart.
the lattice energy, if it's a small
It's just the
value,
opposite. Then it doesn't take much
the
energy
way
to break
lattice
it apart.
energy is written, we go this direction.
It's just
do
the
this.
opposite.
The way lattice energy is written, so
We
that
go
makes this
A
direction.
small
to
positive
do
value.
this.
Small positive value,
Okay.
large lattice,
So that makes it
large
a small
solvation
positive
energy,
value.
large polarity of the
positive
solvent,
value.
large lattice,
Well, if the
large
solvent has a
solvation
large
energy, large
polarity,
polarity of the solvent.
well, if the solvent has a large polarity,
You know what? That's not a real good question. It's kind of
You know what?
confusing.
Yeah,
That's not a real good question. It's kind of confusing because the answer is supposed to be all the above.
yeah.
They're saying.
Because the answer is
Oh,
supposed to be
you're
all
saying-
the
okay,
above.
gotcha. But you're saying
Yeah.
not very good. They're
I
saying-
know the energy's, it's supposed to be all the
Oh, you're
above.
saying, okay, gotcha.
Large
You're saying not
magnitude
very
of
good.
solvation. I know the energy's, it's supposed to be all the
Yeah,
above.
it draws them together.
Large magnitude of solvation energy of the
large solvation energy here.
Yeah, it draws them together. Small magnitude of lattice energy. of the
Large
solute.
solvation energy here.
Small
What we
magnitude
learned
of
was-
lattice energy. of the
Okay.
solute.
If this is large, what we learned was, okay,
No,
If
it
this
still
is
doesn't make
large-
sense.
If that shows up on the test, then
No, it still doesn't make sense.
I'll deal with it then. If that shows up on the test, then I may just give that.
I'll deal
one to
with
you.
it then.
I may just give that one to
at
you.
one time, it probably made sense. Not today. At one time, it probably made sense. Not today.
Let's go on, number 6.
In fact, I don't know why
Let's
that
go
one's
on,
in the
number
easy
6.
section. Okay, solid
In fact,
KF
I
has
don't
a
know why
lattice
that one's in
energy
the
of
easy
minus
section.
804.
You know what? I'm gonna cheat.
Okay, solid KF has a lattice energy of minus 804.
You know what? I'm gonna
see how I
approached it. I want to see how I approached it. Here we go. Oh, that number 5. Here we go. I sent you to a textbook. That number 5,
And that's the wrong textbook.
I
because
sent
you
you
don't
to
have
a
a copy of
textbook.
this one.
So supposedly there's
Yeah,
there's
and that's
some
the wrong
discussion of it
textbook, because
in
you don't
your
have a copy of this one.
Brown. So supposedly
Could you
there's
find
there's some discussion of it in your
No.
okay. Brown. All right.
Could you find it?
So this next one,
No.
okay.
Just so I don't
All right.
stumble around.
So this next one, just so I don't
Solid
stumble
potassium
around.
fluoride has a lattice energy of minus 804 and a heat of solution in water of
Solid
minus
potassium
15. Fluoride has a lattice
Rubidium
energy of minus
fluoride,
804
which
and a heat
is
of solution in water of
the-
minus 15.
The alkaline metal
Rubidium
just below
fluoride,
potassium, which
We
is
form a fluoride with that one.
the
Has a lattice
the
energy of
alkaline
minus
metal just below
768
potassium.
and a heat of solution
form
of
a
minus
fluoride
24.
with that one. Which salt
Has
forms
a lattice
stronger
energy of
attractions
minus
with water.
768 and a heat of solution
Well,
of minus 24.
Which salt forms stronger
If we look
attractions
at
with water?
KF,
Well,
let's see, KF.
if we look at,
If we say the lattice
KF,
energy, let's see, KF. Of KF, if we say the lattice
is equal
energy.
to,
Let's see, KF.
lattice energy is minus
equal to
804
Let's see, KF.
kilojoules per mole. Lattice energy is
What does
minus
that mean?
804
What we're saying is that the
kilojoules
K
per mole.
ions
What does that mean?
and the F ions.
What we're saying
as a
is
gas
that the
come
K
together
ions to form
and the
F
KF
ions
as a gas come together.
That's what that means.
to
So it's going
form
to give up that much
KF
energy when it does this.
solid.
That's what that means. So it's going to
Whereas the
give up that
rubidium-
much energy when it does this. Fluoride, delta H.
Whereas
lattice,
the rubidium
is equal, fluoride.
Yeah.
Delta H lattice.
is equal.
Yeah, so this one has rubidium plus fluoride. So this one has rubidium plus fluoride. If we just look at this and reason it out, rubidium, fluoride. If we just look at this and reason it out.
Rubidium is a bigger ion.
They've got the same charges, a negative, a positive.
Rubidium is a
negative,
bigger
positive.
ion. Remember,
They've got the same
bigger
charges,
positive
a
ion
negative,
here
a positive,
keeps those
a negative,
charges,
positive.
the centers of
Remember,
charges further away from
Bigger
each other.
positive ion.
So you ought to
here
get less
keeps those
energy
charges
back. The centers
from
of
this
charges
one.
further away from each other. So you ought to get less energy back.
in this process
this
than
one.
you do from that one.
And that's true.
You don't get as much energy
in this
process than you do from
Because
that
the
one.
ions are
That's
further
true.
apart.
You don't get as much
All right,
energy
now,
back.
Because the ions are further apart.
Which salt forms
All right,
stronger
now-
attractions with water?
Well, the stronger attraction with water,
Which salt forms
we
stronger
want to
attractions with
know
water?
well, the stronger
heat
attraction
of
with
hydration.
water, we want to know the
So I
heat of
expressed it this
hydration.
way. The delta H of
So
solution.
I expressed it this way.
Is equal to these
steps.
steps. Delta
Right.
H of solution.
We're gonna,
These aren't exactly
equal
the
to
same
these
ones
steps.
as we were discussing in
Right.
class.
and we're gonna,
These
Right,
aren't
in this
exactly the
case,
same ones
this
as
is
we
the,
were discussing in class.
lattice energy.
And
Right.
in this case,
For the lattice
this
energy,
is
let's
the,
see,
get these
lattice
ions
energy
apart from the solid.
and for the lattice energy,
that
let's
lattice
get
energy
these
is going to be
ions
the
apart
opposite of this
from the
value.
solid. This is the ions coming
That
together.
lattice energy
We want
is
to get
going
them
to be the
apart, so we have
opposite
to
of this
actually
value.
add. This is the ions coming together.
This is going to be
We
negative.
want to get them apart, so we have to actually add.
Delta H for the lattice. This is going to be
For each
negative.
one.
That's what delta H1 is going to be. Delta H for the lattice.
Whereas
For each
this
one,
one, these
That's
two
what delta
together,
H1 is going to be.
right?
Breaking
Whereas
this one, these
making
two
a
together,
hole and then solvating,
breaking
them. Making a hole and then
let's see, we call this solvent
solvating them.
expansion. Let's see, we call this solvent expansion. And we call this one solvation energy. And we call this one solvation. This is where
energy.
the separate ions come together with the molecules.
This
of
is
water.
where
the separate
This is where
ions
we
come
break
together
the
with
bonds between two
the
water
molecules of water.
so that you can make
This
the
is
other
where
bonds.
we
break the bonds between two water molecules.
But
so
this
that
is
you can
also
make the other
referred
bonds.
to as the heat of hydration. But this is also referred to as the heat of hydration. Okay. Okay. Now, this thing right here is the same for both of them. Right, that's constant. That doesn't
Now,
change. This
is
thing
the
right
one that
here
makes
is the
the
same for both of them. So the heat of
Right,
hydration.
that's
constant. That
If we
doesn't
can
change.
determine what this
This is the one that
then
makes the
that will
difference.
tell us the difference
So the heat of
between
hydration,
these two.
If we can determine what this
KF
is,
and this one
then
for
that will
R.
tell us the difference
RBF.
between these two.
And
This
this one
this
for
is also
KF
KF and this one for R.
So we're given
RBF.
also the
And
heat
this
of
is
solution.
also different. So the heat of solution.
So we're given also the
For one,
heat of solution.
heat of solution for.
So the heat of solution
For one,
solution.
the heat of solution for.
Well, let's see, I'm doing the same thing I did before. Solution.
All right, so let me move this
I'm
and
spreading,
write it
I'm
over here
doing
on
the
the
same
right-hand
thing I did
side.
before.
So
All
the
right, so let
heat
me
of
move this
solution
and write it over here on the right hand side.
for KF.
So the heat of solution
is equal to, for KF, minus 15 is equal to
kilojoules per mole.
minus 15.
Minus 15 kilojoules per mole.
Kilojoules per mole.
Minus
And the heat of
15
solution for rubidium
kilojoules per mole. And the heat of solution for
Is minus
rubidium fluoride
24.
minus 24.
Is
kilojoules
minus
per mole.
24.
Okay.
Minus 24.
Now that is equal to
kilojoules per mole.
the lattice energy. Now that is equal to the lattice energy.
Delta H lattice for KF. The delta H lattice for
KF.
RBF. The delta H lattice for
Plus
The heat of
RBF.
hydration. Yeah,
plus
so the stronger
the
attraction to
heat of
water.
hydration. This solvation energy is
Yeah.
buried
So the
in this
stronger
value.
attraction to
We
water.
really only need
This
the solvation
solvation
energy
for
is
the heat of hydration.
buried in this value. And we really
Because we
only
know
need
the
to solve
difference
this
between
one
the
for
two. The heat of hydration.
is due only to this
Because we know
solvation.
the
energy.
difference between the two.
Is
Okay.
due only to this solvation
far.
energy.
Okay.
All
So
right.
far.
So if we,
All right, actually, this value is going to be negative.
so if we did that already right there.
Actually, this value is going to be
So
negative.
now
What we've got is,
We
for the
did that
next
already
one,
right there.
the KF. So now what we've got is,
For the
minus
next one,
15
KF.
kilojoules per mole. We've got, minus 15 kilojoules per mole.
And this value is going to be,
And, yeah, after we do the
this
minus sign,
value
it's
is
going to
going
be
to
804.
be,
And after we do the minus sign here, it's
Yeah.
going to be
After we do the
768.
minus sign, it's going
So
to be
this is going to be
804.
minus 15, and after we do
Plus
the minus sign here,
804.
it's going to be 768. So this is going to be minus 15 plus 804. Actually, no. Because I'm going to move it on that side.
It makes it negative again.
Actually, no.
Yeah.
Because I'm going to move it on that side.
Yeah, it makes it negative again.
It's positive on this side,
Yeah.
but I'm going to solve for this one. So
Yeah,
we'll move it
so
on that side.
it's
It's
positive
positive
on
on
this
this side. This is equal to the heat of
But
hydration. I'm going to
hydration.
solve for this one. So we move it on that side, makes it positive. And
This is
for
equal to
rubidium
the heat of
fluoride,
hydration.
it's minus 24. And
Kilojoules
for
per
rubidium
mole.
fluoride, plus 768 minus 24 equals the heat of
Kilojoules per
hydration
mole.
for that one. Plus 768. Now
Equals
just
the
the heat of hydration for
Minus
that.
15 and 804 is what?
Okay. Now just the
Minus 15 and 804 is what?
1 is 8, 789 kilojoules. And 1 is 8,
Oh, excuse me.
789 kilojoules. That was positive. This is negative. I'm sorry.
Oh, excuse me.
That's my
Uh,
mistake. That was positive. This is
negative,
negative. I'm
because
sorry. We made it positive over here because
That's
of
my
the,
mistake.
the
Negative,
chemistry
negative,
involved.
because
We made it positive over here because
the
of the
equation.
the, but now
Chemistry involved.
mathematically, we move that positive over here on the
we put the
negative. So now
equation.
it's 804
But now,
plus 15. Mathematically,
So
we
it's
move that
819,
positive over
right?
here on the negative. So now it's
KF.
804 plus 15.
That's a negative.
So it's 8,
And then a
right?
negative for KF.
Let's see, 2, and then a negative 1 and 8's 9, 792.
So the heat of hydration is much stronger for KF. The solvation energy
So the heat of
hydration is much stronger for
because this is
KF.
more negative than that one.
The solvation energy is higher for KF because this is more negative than that one. To get what?
How'd you get 819? How'd you get that percentage?
804 plus 15.
To get what?
How does it get 8?
Well, minus 804 minus 15. 804 plus 15 is a minus 819. Well, minus 804 minus 15 is a minus 819. Correct? Are we good? Okay. And I did the same thing for this one. So what that tells us is KF has a higher. Okay. And I did the same thing for this one. So what that tells us is KF has a higher.
KF has a stronger attraction for water.
Let's see. It's a stronger hydration energy.
KF has a stronger
Because it
attraction
gives
for
up more
water
energy. It's more negative. It's a stronger hydration energy.
when we come together.
Because it gives up more energy. It's more negative.
When we come together. More negative heat of hydration.
Yep. That's the value we were determining right here.
More negative
This
heat of hydration.
Yep. Well, that's the value we were determining right here. This heat of hydration. Well,
That took too long.
We do have 15
Okay.
minutes left.
That took too long.
We do have 15 minutes left. Is the lab long?
Not particularly.
Okay. Is the lab long?
Not particularly.
Okay.
Let's see, 7.
Use the following drawing of a gaseous
Let's see,
solution
7.
in equilibrium with a solution. Use the following drawing
Gaseous
of a gaseous
solute
solute
in equilibrium with a
in
solution.
equilibrium with a
To help
solution.
answer the question below.
Gaseous solute in equilibrium with a solution to help answer the question below.
The piston is pushed
So-
downward.
So what's going to happen? Well, the
The
gas is
piston
going
is
to become
pushed
more
downward
soluble in the.
So what's going to
liquid.
happen?
Well, the gas is going to become more soluble in the.
This will cause the pressure of the gas to increase, yes. And the concentration of
This
the
will cause
dissolved
the
gas to
pressure
go
of the
up.
gas to increase.
Yes. And the concentration of the
I think that's
dissolved
Henry's
gas to
law.
go up.
I think that's Henry's law. 8. Which of the following correctly states the relationship between temperature and solubility of a substance in water? 8. Which of the following correctly
Well,
states the relationship between
solids
temperature and
generally
solubility of a substance
become
in
more
water?
soluble.
Well, there are exceptions.
Solids
The
generally
gases always
become
become
more
more
soluble.
soluble. There are
So,
exceptions.
the
The gases
solubility of the
always become
substance
less
C.
soluble. In water with temperature cannot be
So,
accurately predicted,
the
especially
solubility
for
of the
ionic solids.
substance
Well, that's
C.
true. In water with temperature cannot be accurately predicted, especially for ionic solids. Well, that's true.
Okay,
No.
Okay,
B, they're wrong.
B,
Solubility D, a substance in water decreases as
No,
temperature
A,
lowers.
B, they're wrong.
Solubility
especially for
D, a
gases.
substance in water decreases as temperature lowers.
No, solubility of gas increases
Especially
with
for
the decreasing
gases.
temperature.
So C is the only
No,
one. that works for
solubility
that.
of gas increases with the decreasing temperature. So C is the only one that works for that.
Let's see, 10. Let's see, 10.
A solution contains 1 mole of liquid A and 3 moles of liquid B. This solution
a solution
has a vapor
contains 1
pressure
mole
of
of liquid A
314
and 3 moles of liquid
425.
B. Okay,
This
the solution
solution
has
has
a
a vapor
314
pressure of
torr at 25
314
degrees.
torr at 25. The
Okay,
pure
the solution
has liquid
314
A
torr at
has a
25
vapor
degrees.
pressure of 265. And the pure liquid
the
B
pure
has a vapor pressure of
liquid A
355. Has a vapor pressure of 265.
Okay, I
and
think
the
this
pure
one needs a
liquid B
picture.
has a vapor pressure of 355. Which of the following is true?
Okay, I think this one needs a picture.
All right. So let's see, A is increasing to the right. And
Right.
B is increasing
So let's
to the
see,
left. A is increasing to the right. And B is increasing to the left. A has a vapor pressure of 265 when it's pure. So A has a vapor
265,
pressure
let's
of
put it down here.
265 when it's pure.
265 torr.
265, let's
Is
put it down
A.
here, pure A.
265.
And pure
torr.
B has
Is A.
3 pure A. 55. And pure B has 3 Okay,
55. Now, if we have 1 mole
Okay.
of A and 3 moles of B. Now, if we have 1.
So what's that
mole
ratio?
of A and 3 moles of B.
1/4.
1/4
So
of
what's
A
that
and
ratio?
3/4 of B.
So 1/4 of A
1/4.
would be down here
1/4 of A and 3/4 of B.
and 3/4 of B.
So
would be
1/4 of
down
A
here.
would be down here.
So it should be somewhere in here, right? If we
And
drew a line
3/4 of
between
B would
there,
be down here.
it should be,
So
so it
about
should
here.
be somewhere in here, right? If we
Right,
drew a line
around
between there,
300 or so.
it
forward.
should be about
We
here.
would expect.
Right.
Around 300 or so. Forward. We would expect.
The solution has 314 torque pressure. The solution
so
has
let's go back to-
314 torque pressure.
The pressure of the solution.
All right, so let's go back to
Is equal
The,
to
the
the pressure
modified.
of the solution. So we need the mole fraction of
Is equal
A
to the modified.
times the pure A. So we
Plus
need
the
the
mole
fraction of
B
A
times the pure
times the
B.
pure A plus the mole fraction
So
of
the
B
pure B
times the
pure
pure A.
We can calculate what we would expect if
So
it were
the pure
ideal.
B, pure A, we can
So
calculate
the
what we
vapor
would
pressure
expect. A
if it were
is
ideal.
265 when it's pure, but it's
So
only
the
mole
vapor
fraction
pressure
of A
1 in
is
4,
265
right?
when
0.25.
it's pure,
But it's
Correct.
only a mole fraction of 1 in 4, right?
Yeah,
0.25.
0.25. Correct? And B is
Yeah,
0.75 mole fraction. Times its, and B
Pure,
is
355.
0.75 mole fraction.
So we would expect,
Times
have to do
its
some calculations.
pure, 355.
We would expect,
So we would expect
0.25 have to do some
times
calculations.
265.
We would
is,
expect
0.25
0.25
times 265
0.75
is
times 355
66.25 and then 266, add those two
0.75
together, times 355.
We would expect the value to be
is 266, add those two
3.
together, 4. We would expect the value to be 333,
right,
4. So we would expect it to be that, but it's not, it's higher.
right.
So
The
we would expect
true-
it to be that, but it's not, it's higher. Solution pressure is 350.
5.
Solution pressure is 350 compared to 333.
5.
So that's a positive deviation
What does that mean?
compared to 333.
Well,
So that's a positive
we don't have to
deviation.
answer the question.
What does that mean?
The solution exhibits a
Well,
negative deviation from
we don't
Reynolds
have
law. To answer the question.
Yes,
The solution exhibits a
Uh,
negative
a minute.
deviation from Reynolds law.
yes.
I put the wrong
Uh,
verb. It's
Wait a minute.
314.
I'm sorry. 314.
I put the wrong verb. It's 314.
That's
I'm
the
sorry.
measured value. 314.
This is the expected value. It has a negative deviation.
That's the measured
This
value.
is below what
This
we
is
would
the expected
expect.
value.
It
It's
has a
actually
negative
down in here
deviation.
somewhere, so we're getting
A curve
this is
like that.
below what we would expect.
It's a
It's
negative
actually down in here
deviation
somewhere,
for
so we're getting
Reynolds
the,
law. A curve like that.
okay?
It's a negative deviation for you from Reynolds law.
Okay? Ten,
12.
10,
A cucumber is placed in a
12.
concentrated salt solution. What will most likely happen? A cucumber is placed in a concentrated salt solution. What will most likely
Concentrated salt
happen?
solution has a higher osmotic pressure than inside the cell.
Concentrated
Right, so
salt
the water's
solution
gonna
has a
move
higher
out
osmotic
of the
pressure
cell.
than inside the cell.
All right, so the
Water will
water's gonna
flow
move.
from the cucumber to the
cell.
solution. Yep, that's it. A. Water will flow from the cucumber to the solution.
13,
Yep, that's it. A.
13.
Osmotic pressure depends on all but the following.
Well, let's see. What's the formula?
Osmotic pressure depends on all but the
So
following.
we have
Well, let's
molarity
see.
What's the
Times the
formula?
gas constant
Times temperature,
So
right?
we
We have molarity times the gas constant
So
times
It
temperature,
depends
right?
on pressure.
No,
there's no pressure in there. So
It depends
all
on
but
pressure.
pressure.
Atmospheric pressure is
No,
not
there's
in
no
the
pressure in
calculation. Molarity is, temperature
All but which
is,
of the following. Atmospheric pressure is
ratio
not
of
in the
moles of
calculation.
solute solution volume.
Molarity
is, temperature
Well, that's
is,
Molarity.
ratio of moles of solute
So
solution
yeah, A
volume.
is the one that doesn't
well,
fit.
that's,
Doesn't matter what the
molarity.
atmospheric pressure is. So yeah, A is the one that doesn't fit. Doesn't matter what the atmospheric pressure is.
at least it's not an oven in here today.
At least it's not an oven in here today.
Shaving cream is an example of which colloid type? It's a
That's D.
gas and a
Shaving
liquid cream is an example of which
foam.
colloid type? It's a
That's D.
gas and a liquid,
It's a foam.
Vodka's not the
moderate,
Yeah.
Vodka's not.
moderate.
Now we're at a moderate. Actually, we've done
Some that were actually difficult. They're in the easy section.
Now
They
we're at a
shouldn't be there.
moderate. Actually, we've done some that were actually
Difficult.
Number
They're in the
3.
easy section. They shouldn't be
three
there.
moderate.
A 0.2
3.
molar solution of
Three
solute
moderate.
X in benzene displays an osmotic pressure given by
A
the formula.
0.2
molar solution of solute
I
X in benzene displays an
equals
osmotic pressure given by the
0.1.
formula.
I RT equals 0.1.
Okay. Which of the following is most likely to be the
RT.
case?
Well, if it starts out at a
Okay.
molar concentration
Which of the following is most likely to be the case?
Well, if it starts out at a molar concentration of 0.2, concentration of X, then
Yeah.
what happens to go here?
Well,
Concentration of X,
this,
and this, then what
and we
happens
put
to
our
go here?
Van Hoff
Well, if we
correction
do
in there.
this, and this, then
And we put
these
our
two
Van Hoff correction
together
in there.
are 0.1.
And
And
molar.
these two together are 0.1
times the molar, which is 0.2.
and the molar, then I would have to be what?
Be
1/2
times the molar, which is 0.2.
Then
Well,
I would have to be what? 1/2?
One, we normally think in terms of whole numbers. So if it's one, then there's no dissociation. We normally
there's
think in
two
terms of whole
associates
numbers.
into two particles.
So if it's one,
But if we
then there's
put it
no
in solution
dissociation.
at 0.2,
If there's two
and it gives us
dissociates into
0.1
two
multiplier,
that
but if we
means
put it in solution at 0.2,
for every
and it gives us
two we
0.1
put in, we get
multiplier,
one in solution.
that means
they're attaching to one another.
for every
Two we put in, we get one
X
in solution.
exists in benzene
attaching
as
to one
X2.
Right?
X
We get
exists in
an ion
benzene as
pairing, so to
X2.
speak. Right? We get
an
some type of
ion
association,
pairing
so to
where you're
speak,
pulling two of them together.
and
We
decreasing
get
its some type of
concentration from
association
0.2 to
where you're
0.1.
pulling two of them together.
That makes sense? And decreasing its concentration from 0.2 to 0.1. That was 3. That makes sense?
4.
Okay. That was 3.
4. I need another change. Oops. I need another change.
Which of the following solutions? 0.1 molar sodium chloride.
Molal.
Which of the following solutions?
Molal.
0.1 molar sodium
chloride.
chloride.
Molal.
0.1 mol
Sodium
glucose.
chloride. 1.5.
0.1
glucose.
molal glucose.
0.15.
0.1 molal.
glucose.
0.1 molal
Calcium chloride.
would have the
Molal.
okay,
Calcium
highest vapor
chloride.
pressure, lowest boiling point. Would have the
All
okay,
right, this is
highest
gonna
vapor
be
pressure, lowest boiling
The
point.
equivalent of 0.2 molal.
All right,
ions.
this is going to be
The equivalent of
0.15.
0.2 molal ions, glucose, because it doesn't dissociate.
This is going to be 0.15.
This one's going to be 0.3
Molal.
because it doesn't dissociate.
Molal
Ions. And this one's going to be 0.3
So the
molal.
vapor
ions.
pressure is going to be highest for
This one.
so
It has the
the
lowest
vapor
concentration.
pressure is going to be highest. It will
for
have the
this
least decreasing effect
It has the lowest
on the
concentration.
solution. It will have the least.
As you increase the
decreasing
concentration
effect
in solution, you
on the
decrease the
solution.
vapor pressure.
As you
So this
increase
one
the
would have the least
concentration
effect. In solution, you
Right.
decrease
Isn't that
the
what it
vapor
said?
pressure.
highest vapor pressure,
So this one would have the
would
least
be-
effect. This one because it has the
Isn't that what it
least
said?
effect on the
highest
pure
vapor pressure solute.
would be this one because
How
it has
about
the least
the
effect on
lowest
the
boiling
pure.
point solute. We're gonna, how about the lowest boiling point?
It'd be the same one. We're gonna,
Right.
the least concentration of this will affect
It'd be
the
the same
boiling
one.
point the least.
Right.
Boiling point
The
depression.
least concentration of this
is
will
the
affect
effect
the
that
boiling
a
point
solute
it
has
has
on
on
it.
it. Boiling
This
point
is the least
depression
concentration.
So glucose
Is the
both of
effect
them.
that a
D.
solute has on it. This is the least
Okay.
concentration.
So glucose is both of them.
D.
Oh, got another one. Okay.
Is it the same ones? Same
Oh,
ones?
got another one.
Same ones. See, this is gonna be 5. Is it the same ones? Same ones?
Lowest
ones.
vapor
See,
pressure.
this is gonna be 5. The lowest vapor pressure is gonna be the one
Lowest
with the
vapor
highest
pressure.
concentration. So now we got this one. The lowest vapor pressure is going to be the one that with the highest concentration. So now we got this one. Would be the lowest vapor pressure. Lowest boiling point would then be glucose. Would be the lowest
Calcium
vapor
chloride
pressure.
glucose would be the answer.
Lowest boiling point
C.
would then be glucose. So calcium
Okay.
chloride.
Chloride glucose would be the answer. C. We're in the difficulty now.
We're just coming to the home stretch.
We're in the difficulty now.
We're just coming to the home stretch. Difficult. Number 2.
A solution is prepared from
Number
53.8 grams of a non-volatile, non-dissociating solute. A solution is
85
prepared from
grams of water.
53.8 grams of a
pressure of the
non-volatile,
solution
non-dissociating
is 60
solute.
degrees
And
at
85 grams of
132
water.
torr.
The vapor pressure of
The
the
vapor pressure of water at
solution is 60 degrees.
What's the molar
At
mass of the solute?
132 torr.
Okay,
The
this
vapor
needs a
pressure of
picture.
water at 60 is 150. What's the molar mass of the solute?
Okay, this needs a picture.
What do we need to know the molar mass?
That's right.
What do we need to know?
We need to know the
molar
mass of the solute. And we need to know, that's
the
right,
number of
moles. We need to know the mass of the
Of the
solute. And
We
we
know the
need to
mass,
know the number of
53.8
moles.
grams.
That's given.
Of the solute. We know the mass,
We need to find out the
53.8
number of
grams.
moles.
That's given. So.
We need to find out the number of moles.
The vapor pressure of the solution
So,
at 60 is 132. The vapor pressure of the solution at 60 is 132. Of water at 60 is the vapor pressure
50.
of water at 60 is
Okay.
150.
Okay.
I'm gonna have to cheat. My mind's slipping this late in the day. I'm gonna have to cheat. My mind's slipping this late in the day. So difficult. So difficult. Here we go. Here we go.
Okay. So the vapor pressure of the solution is equal to the vapor pressure of the solution
132
is
torr.
equal to
132 torr.
that's equal to the mole fraction of water. That's equal to the mole fractions, the pure vapor pressure of water times. So the pure vapor pressure of water is 150. So the pure vapor pressure of water is 100. So we can find out the mole
50?
fraction of water.
Yep, 150.
So we can find out the mole fraction of water is equal to 132.
So mole fraction of water
divided by 150 is equal to 132
Mm-hmm.
divided by
because it's
150. Mole fraction times 150 equals 132.
It's
So
still
mole,
makes it heavy.
yeah,
I'm sorry.
because it's mole fraction times 150 equals
Yeah.
132.
It still
a
makes
mole-
it heavy.
I'm sorry?
Let's see, 132 enter
Yeah.
150.
Let's see,
So
the mole fraction of
132
water is
enter
0.88. Divide.
So
So
the
mole fraction of water is 0.88.
Do they give it
So mole fraction,
they just call it anything.
so let's say X. No,
Do
let's,
they give it a,
that gets confused with the other.
They
Let's
just
say
call
mole
it
fraction.
anything.
So let's say X. No, that
Is
gets
equal to
confused
1
with the other.
minus
Say mole
0.88.
fraction of A. Or 0.12,
is equal to 1 minus 0.12, right? That's
or
the mole
0.12, right?
That's the mole fraction.
let's see. Let's see. I'm sorry? I'm sorry?
Well, if the mole fraction of water is 0.88, then the mole fraction of the A has to be what's
Well,
left over. If the mole fraction of water is 0.88, then the mole fraction of the A has to be.
Now, we can
what's left
calculate how
over.
many moles of water are in there,
No need,
right? 85
Okay.
grams of
Now,
water.
we
We can calculate how many moles of water are in there,
no need.
right? 85 grams of water.
Grams per mole.
85
This
grams
is
of water.
18.02.
85 divided by 18.02.
18.02
85 divided by
Is
18.02
4.72 moles,
is 4.72.
4.72 moles
Let's see.
of
I
water.
think we need to use a little algebra here. Let's see. I
Let's
think
do
we need
this.
to use a little
The mole
algebra
fraction
here.
of water is this, which means it's the moles of
Let's
water.
do this.
The mole fraction of
Divided
water
by
is this, the moles,
which
which
means
means
A
it's the moles
plus
of
the
water.
moles of
Water.
Right,
Divided
total moles.
by the moles of A.
We
plus
just
the moles
calculated
of
moles
water.
of water. Right, total moles.
Right, so this one is 4.72.
We just calculated the moles
This
of
one
water.
is 4.72.
Right,
so this one is 4.72.
Yeah, we can count, we can solve
This one
that
is
now.
4.72, okay? So,
Yeah, we can count, we can
I'm
solve
starting to
that
get messy
now.
again. Okay,
So best of the.
So, I'm starting to get messy again.
Yeah,
I didn't need this one after all.
Best of the two done something.
Yeah, I didn't need this one after all. So if you solve this one for, NA. Right,
So
you
if you
take
solve
this
this
whole
one
group
for,
times 0.88,
NA,
and then you factor it out and you
Right,
keep
you take
the
this
NA on
whole
one
group
side.
times
0.88.
you know, do your
And
algebra
then
trick.
you factor it
Right.
out and you keep
And we
the
should
NA
come
on
out
one
with,
side.
You know, do your algebra trick.
0.6432. And we should come out with 0.6432.
Now we got a value here. 0.6432. Now we got a
Divided
value
into
here.
53.8. Should give us
0.6432
Divided into
grams
53.8
per
should give us
mole.
83.6.
grams per mole.
We had to take the information we got.
To figure out what goes in here.
We had to
I
take
can-
the information we
mole.
got.
I'm sorry, to figure out what goes in here. Right, and the mole,
I'm sorry,
0.643.
2.
Okay, I'm running late. Let's see. Number 4. Okay, I'm running late. Let's see.
Can I erase?
Good,
Number 4.
Oh, can I erase?
good.
Now you've got 10.4 grams mixture of table sugar and table salt. Now you've got 10.4 grams mixture of table sugar and
This is gonna
table
take some
salt.
doing too.
When this mixture is dissolved in 150 grams of water,
This
the
is gonna
freezing
take some
point
doing
is
too.
found to be minus 2.24
When this mixture is
degrees.
dissolved
So
in
we
150
decreased
grams of water,
we got
the
a
freezing
delta
point
T
is found to be
for
minus
water, the
2.24
solution
degrees.
of So we
2.24.
decreased, we
What's
got
the
a delta
delta
T by mass of
for
sugar
water,
in the
this
original
solution
mixture.
of 2.24.
All right. What's the percent by
So
mass
we're
of
given-
sugar in the original mixture?
10.4
So we're given
grams. 10.4
Sucrose,
0
plus
grams sodium chloride. Sucrose
plus
and we put it in
sodium
150 grams and we put
water.
it in 150 grams of
Let's
water.
see, are we given the KF? We're not given the KF for water. We're gonna
Hmm?
need that. Let's see, are we
We are.
given the KF?
Are we given
We're
that?
not given the KF for water. We're gonna need that. I don't see it there.
We are.
Not
Are
in
we
the
given that?
problem. I don't see
It's
it
in the
there.
work problem.
Not in the problem.
Right, freezing point depression, we know we're gonna need it.
It's in the
because
work problem.
That was one of the parameters. Right, freezing
So
point depression, we know we're gonna
degrees
need it because
C
that was one of the parameters.
per
Mole degrees, and we know that the
C
change in temperature
per
for freezing point
mole
is 2.24. And we know that the change in temperature for freezing point
right?
is 2.24 degrees C.
We know that this is gonna dissociate.
So the Van Hoff correction here is going to be.
We know that this is gonna dissociate.
Let's see,
So the
the
Van
I
Hoff
for
correction here is
sucrose-
going to be,
let's see, the I for sucrose is going to be 1 and the I for sodium chloride is going to be 2. The I for sucrose is going to be 1 and the I for sodium chloride.
we're gonna need to know
It's
the
gonna be
molar
2.
mass of sodium chloride too. We're gonna need to know the
So
molar mass of sodium
Sodium
chloride
is
too.
20
23 and 3545 chlorine, so the molar mass
Sodium is,
58, 23 and 3545 chlorine, so the molar mass is.
Is sucrose given?
44 grams per mole.
No, the formula is
And
given.
it's
Is
so
sucrose
we
given?
do, carbon.
No, the formula is given. 12.01
So we
times
do,
12, 22 times 1.01, and 11 times 16. Add those all together. 12, 22 times 1.01,
sucrose.
and 11 times 16. Add those all
Molar
together.
mass is 342.3 grams per mole. Molar mass is 342.
We're gonna need that.
Grams per mole.
All right. So we know that this
We're gonna need
total
that.
is 10.4.
All right.
So we're gonna let, so we know that this
Since
total
the question is,
10.4.
what's the percent
So we're
by
gonna
mass
let-
of sugar?
Since
So let's let, the question is, what's the percent by mass of sugar?
X, so let's let X
equal the mass of sucrose. Let X equal
That
the
means
mass
that,
of
sucrose.
10.4 minus
That means
X
that,
equals the mass
10
of sodium chloride. Minus X equals the mass of sodium chloride.
all right, so the change in temperature is a
All right,
combined
so
effect.
the
The
additive
change
effect
in temperature
Of the sucrose and the sodium
is
chloride.
a combined effect, an additive effect.
So what we can say
of
is sucrose
that the
and
change
sodium
in temperature
chloride
separately.
is
So
due
what we can
to
say is that the
change in temperature due to sucrose.
is due to
That
change in
whatever that
temperature
effect is, due to
plus the
sucrose.
change
Change in temperature due to sodium
that
chloride.
value, whatever that effect
Now we can
is.
expand these.
Plus
Plus the change in temperature due to.
Change in temperature
sodium
from
chloride.
sucrose is
Now we can
this,
expand these.
I for change in
sucrose.
temperature from sucrose,
Right,
the
is
Van Hoff
this,
correction.
I
I for
times,
sucrose,
right,
the Van Hoff correction
KF
for
times
water, the
times the
KF
molality of
for
sucrose.
water,
Times the
plus
molality
the change
of
in temperature
sucrose.
due to sodium chloride,
which would be I for sodium chloride,
plus the change in temperature due to sodium
KF
chloride,
for water,
which would be I for
and
sodium
the
chloride,
molality of sodium
and the
chloride,
KF for water.
and the molality
That
of sodium chloride.
formula tells us this temperature is due to this
That
effect
and that effect.
formula tells us this temperature is due to this effect. All right, so if we
that
put the
effect.
values in there. I'm sorry? All right, so if we put the values in there. I'm sorry? Right, 2.24 degrees over here. And this I for sucrose is 1. Right, 2.24
And then the
degrees over
KF is
here.
1.86.
And this I for sucrose is
Right, for both
1.
of them, actually.
And then the
And the
KF is
molality
1.86 of the sucrose
Right,
is
for
the
both of them,
moles of
actually.
sucrose. And the molality of the sucrose is the moles of sucrose. Per, not here, 0.150 kilograms. Not here. 0.150
mass.
kilograms. So this is 0.150. It's moles per mass.
On this side, we've got 2.
So this is
and
0.150.
1.86. And
On
this
this
is
side,
the
we've got
moles
2
of sodium chloride.
and 1.86 per.
And this is the
0.150.
moles of sodium chloride per
Okay.
0.150.
All right, so if we solve this whole equation for
All right.
moles. So if we solve this and we
whole
keep this
equation
2 for moles.
2 times that one and 1 times
and we
this
keep
one, then
this
we can
2,
factor
these
2
things
times
out.
that one and 1 times this one, then we
Right.
can factor.
We can factor
these
1.86
things
out.
Factor 1.15 out.
Right? We can factor
And
1.86
that would
out,
put
factor
1.15 out.
1.86 divided by
And that would put,
0.15.
now that
1.86 divided by
moles of
0.15.
sucrose,
Now that
times moles of
plus-
sucrose, excuse me,
plus
2 times moles of sodium chloride.
plus,
Excuse me.
so we just factored out
2
these 2
times
things right here,
moles of
1.86.
sodium chloride. They're both common to these
So we just
expressions. so we can
factored
put them
out these
outside
2
like
things
that.
right here, 1.86 Okay,
They're both common to these expressions, so we can put them outside.
so now if we
that.
solve for,
For
okay,
this one, and this is still equal to.
so now if we solve
2.24.
for
For this, bring that over here, and this is still equal to 2.24. Then that's
So if we bring
two
that over
point
here,
two four times 0.150.
And that's
2.24 over 1.86 times 0.150. That's equal to moles of sucrose, 1.86 plus 2 times moles. And that's equal to sodium chloride. Moles of sucrose plus 2
Okay.
times moles of sodium chloride.
okay, all right. So,
This expression here reduces to 0.1806.
so
This expression
And this
here
expression,
reduces to
moles of sucrose,
0.1806.
would be the
And
mass
this
of
expression,
sucrose,
moles of
X,
sucrose divided by
would
its
be
molar mass.
the mass
So
of
this would be
sucrose,
X divided by 3 divided by its
3.
molar mass.
So this would be
This would
X
be,
divided by 342.
10.4 minus X,
Only
this
it's
would
times
be
2.
10.4 minus X,
Only it's times 2. Yeah,
plus 2
Yeah.
times 10.4 plus minus X divided by its
2
molar mass times 10.4 minus X divided by its molar mass, 58.44.
so now what we need to do is
There we go.
solve for X. So now what we
Right,
need
so
to
if
do is
If we resolve that X,
solve for X,
which
which
is
is another
another
2 or 3 steps.
if we resolve that
The
X,
X
should come out to 5.
Which is another 2 or 3 steps.
The X should come out to 5.60 grams of sucrose.
Oh, and the question was percent by mass.
Okay, so percent by mass then for
Oh, and the
sucrose
question
would be
was
5.6
percent by mass.
divided by 10.4.
Okay,
So
so
percent by mass then for sucrose would be 5.6 divided by 10.4 times 100, which should be equal to 53.8%, which should be equal to 53.8% sucrose. There you go.